40 kilograms of water every single second. This is the astonishing amount that NASA's Swift Observatory detected being expelled from the comet 3I 2023 Atlas in late July and early August. This immense water loss was not occurring when the comet was closest to the Sun, at its perihelion, when it would be maximally exposed to solar radiation. Instead, it happened at a distance of 2.9 astronomical units, nearly 3 times farther from the Sun than Earth. At this range, water should be sublimating at a negligible rate. Furthermore, in less than 3 weeks, the comet would vanish behind our star, hidden from every Earth-based telescope, precisely when observations would be most critical. If you wish to remain informed about subsequent developments, please activate the like button and subscribe. In the comments section, share your geographical location, the current time there, and whether you believe this phenomenon is merely an extreme cometary outburst or something entirely different. Chapter 1. The Mystery of the Fire Hose. The Swift observations published on September the 30th in Astrophysical Journal Letters are not simply unusual, they defy conventional understanding. Dennis Boditz and his research group at the University of Oregon dedicated over 2 hours to processing ultraviolet exposures, aiming to detect the hydroxyl signature, that faint glow emitted when sunlight disassociates water molecules. What they discovered was a mass loss rate that completely contradicts predictions based on distance from the Sun. At such an orbital range, comets typically exhibit surface activity ranging from 3 to 5%. Comet 3I, says 2023 Atlas, however, displayed at least 8%, nearly doubling the expected activity. The true enigma arises when examining the calculations. The energy input from the Sun at 2.9 astronomical units is insufficient to account for 40 kilograms per second of water being released from a nucleus estimated to be between 5 and 6 kilometers in diameter, unless an alternative explanation is at play. Near-infrared observations from the Gemini South Telescope and NASA's Infrared Telescope facility offered clues. These observations revealed ice debris suspended within the comet's coma, not merely water vapor. These were actual fragments of ice drifting within the cloud of gas and dust surrounding the nucleus. When exposed to sunlight, even at reduced intensity, these icy fragments heat up more rapidly than surface ice due to their higher surface area to volume ratio. Each fragment essentially acts as a miniature steam vent. Hundreds, perhaps thousands, of these scattered throughout the coma collectively contribute to the total water output. The visual effect is that the nucleus itself appears significantly more active than its actual surface activity would suggest. Zexi Xing, the lead author of the study, succinctly stated, "Every interstellar comet encountered so far has presented surprises. Oumuamua was arid, Borisov was rich in carbon monoxide, and now Atlas is releasing water at a distance where we did not anticipate it. Each one is fundamentally altering our established knowledge. The crucial question remains, why are these ice fragments present in the coma in the first place? Did Comet 3I 2023 Atlas undergo a fragmentation event prior to its detection? Is this debris accumulated from millions of years of micrometeorite impacts during its interstellar journey? Or does this represent the typical behavior of comets originating from the galactic thick disk? Perhaps their internal structure is fundamentally different, having formed under conditions vastly dissimilar to those within our own solar system. The timing of these events introduces another layer of complexity. Comet 3I 2023. Atlas faded from Swift's observational range in August, having ventured too close to the Sun for safe observation. However, by early October, the European Space Agency's Mars orbiters were able to observe it during a flyby at a distance of 30 million kilometers. The comet's coma was clearly visible, spanning several thousand kilometers, confirming that the activity was ongoing. The comet continues to shed water as it approaches perihelion, and that word, approaches, is crucial. Currently, 3I 2023 Atlas is entering solar conjunction, placing Earth and the comet on opposite sides of the Sun. Consequently, no ground-based telescope can track it through the Sun's glare. It will reach perihelion on October 29th at 1.36 astronomical units, just inside Mars's orbit, completely concealed from our view. At this point, the solar radiation will be orders of magnitude more intense than what Swift detected. If 40 kilograms per second represented the baseline activity at 3 astronomical units, what magnitude of activity can be expected at 1.4? The established scientific consensus predicts a straightforward outcome. The comet should brighten considerably, its coma should expand significantly, and highly volatile ices, such as carbon dioxide and carbon monoxide, which sublimate at lower temperatures than water, should be ejected explosively into space. The comet's tail should elongate into a spectacular streamer spanning millions of kilometers. This pattern has been observed hundreds of times with comets originating within our solar system. However, Comet 3I 2023 Atlas has already demonstrated its propensity to deviate from established predictions. The water activity observed at 2.9 astronomical units was unexpected. The 8% active surface coverage was anomalous. The presence of an icy debris field within the coma was entirely unanticipated. Therefore, the events transpiring during its hidden perihelion passage remain genuinely unknown. The European Space Agency's JWST spacecraft is anticipated to have the most advantageous vantage point between November 2nd and November 25th. Following Comet 3I 2023, Atlas's emergence from behind the Sun, JWST will conduct observations using its cameras, spectrometers, and particle sensors. Its observational perspective will be unique, positioned sufficiently far from the Sun to render the comet visible, while remaining close enough to capture post-perihelion activity in intricate detail. The primary challenge lies in data transmission. JWST is currently employing its high-gain antenna as a heat shield, relying on a slower backup antenna for transmitting data back to Earth. Consequently, the observations acquired in November will not be received until February 2026. This imposes a 3-month waiting period, 3 months of uncertainty regarding whether the comet survived perihelion intact, whether it fragmented under tidal forces similar to Comet Shoemaker-Levy 9 encountering Jupiter, or if something entirely unprecedented transpired during those hidden days behind the Sun. There exists an additional consideration, one that Dennis Boditz alluded to in passing but did not emphasize. Water serves as the universal benchmark in cometary science, the baseline for measuring activity and inferring composition. However, Comet 3I 2023 Atlas is not a native of our solar system. It is a messenger from another star's planetary system, one that potentially formed 10 billion years ago within the galactic thick disk. The protoplanetary disk that gave rise to this object possessed distinct temperature profiles, chemical compositions, and gradients compared to the disk that formed Earth and Jupiter. While the water being detected may be chemically identical to our own hydrogen and oxygen in their familiar configuration, the context is entirely alien. The isotopic ratios, the trace elements present, the very structure of the ice crystals themselves, all these elements contain invaluable information about a star system we are unlikely ever to visit. Swift detected hydroxyl, the fragmented remnants of water molecules. However, hydroxyl can also originate from other parent molecules, such as organic compounds or alcohols, indicating complex chemistry occurring within the coma as sunlight and cosmic rays break down larger molecules into constituent fragments. The 40 kilograms per second release might consist purely of water, or it could be a mixture of water and other volatiles that produce similar spectral signatures. Higher resolution spectroscopy is imperative to ascertain the precise composition. Extended observation windows are also necessary. Crucially, the comet must survive perihelion and maintain its activity as it journeys back towards interstellar space, because that is the other stark reality. Comet 3I 2023 Atlas will not return. After it passes Jupiter in March 2026, it will depart our solar system permanently. This presents our sole opportunity to study a comet from the galactic thick disk, a population of ancient star systems that we have previously had no means of sampling. Every observation holds immense significance. Each data point is irreplaceable. The torrent of water is merely the prelude. It informs us that Comet 3I 2023 Atlas is rich in volatiles, that its structure is unusual, and that it is actively outgassing at distances where solar system comets remain dormant. However, the main event is set to unfold over the next month, concealed behind the Sun, beyond our direct observation, where the established laws of cometary behaviour will either be validated or irrevocably shattered, and when JWST finally transmits its observations in November, when the comet emerges into view, revealing the full impact of whatever transpired during perihelion, we will discover whether this water loss was a mere preview or a dire warning. We will determine if Comet 3I 2023 Atlas is simply an exceptionally active comet, or if it necessitates a complete rewriting of our astronomical textbooks. The answer awaits, concealed, 50 days away from revelation. Chapter 2: Lowe's Mothership Hypothesis. The low scale rating for the object shifted from 4 to 6 within a span of 2 weeks. This is not a minor fluctuation. On a scale where 0 signifies definitively natural and 10 denotes definitively technological, a progression from 4 to 6 indicates a fundamental alteration in the assessment of probability. And Lowe does not implement such changes lightly. Each increment on his scale is predicated on quantifiable anomalies, statistical outliers that resist conventional explanations. By mid-August, Comet 3I 2023 Atlas had accumulated sufficient anomalies to push the needle into territory that causes considerable unease among most astronomers. Let us commence with the trajectory probability that is repeatedly cited and consistently dismissed, 0.005%. This represents the likelihood that a randomly encountered interstellar object would pass as closely to Venus, Mars and Jupiter as Comet 3I 2023 Atlas does. This equates to a 5 in 100,000 chance. Lowe and his team calculated this using principles of orbital mechanics and precise timing windows, factoring in the dynamic nature of planetary motion and the limited opportunities for close approaches. The mathematics are straightforward. An object on a retrograde hyperbolic orbit, entering from the direction of Sagittarius, has an exceedingly narrow probability cone for each planetary encounter. The cumulative probability of intersecting all 3 of these cones is vanishingly small. Critics contend that this is a case of cherry-picking data after the fact, arguing that if one examines a sufficient number of interstellar objects, an unlikely trajectory will inevitably occur by pure chance. While this assertion holds merit, we have only detected 3 interstellar visitors to date, and by sheer coincidence, one of them has navigated a trajectory that grants it access to the 3 most scientifically intriguing rocky bodies within the inner solar system. The initial Bayesian probability for this scenario, the predisposition we should assign before even considering further evidence, is profoundly unsettling. Now let's incorporate the perihelion timing. October 29th, solar conjunction, with Earth and Comet 3I 2023 Atlas, situated on diametrically opposite sides of the Sun. This renders ground-based observation impossible during the most critical phase of its trajectory. If one were intending to execute a propulsive maneuver, an orbital burn to alter velocity, perihelion represents the optimal location. This is where the object achieves its maximum velocity relative to the Sun, meaning every kilogram of propellant yields the greatest possible change in velocity, or delta V. This phenomenon is known as the Oberth effect, and spacecraft utilize it routinely. Coincidentally, Comet 3I 2023 Atlas reaches perihelion precisely when we are unable to observe it. Lowe has calculated the delta V required for small probes released at perihelion to achieve Earth orbit. The numerical results are consistent. A diminutive probe, perhaps weighing 10 kilograms, employing a chemical propulsion system with a specific impulse around 300 seconds, could execute a reverse Oberth maneuver and establish itself in a stable orbit around Earth. The projected arrival window for such probes is late November to early December, precisely when Comet 3I 2023 Atlas is emerging from behind the Sun, and we begin to scrutinize its post-perihelion behavior. Is this the calculated plan? Is there a plan at all? Or are we merely perceiving patterns within randomness, a consequence of our innate human tendency to seek order, amplified by Lowe's framing that primes us to look for precisely these kinds of coincidences? The discrepancy in size remains unresolved. Initial brightness measurements suggested a nucleus measuring 20 kilometers if its albedo were typical for asteroids. This is an extraordinarily large dimension for an interstellar object. Oumuamua measured only a few hundred meters across, and Borisov was less than a kilometer in diameter. The appearance of a 20-kilometer comet in our solar system would represent a statistical anomaly of immense proportions, an event that should realistically not occur within a human lifetime. However, subsequent observations by the Hubble Space Telescope resolved the coma, and the estimated size of the nucleus decreased to between 5 and 6 kilometers based on the brightness of the nucleus itself relative to the overall brightness of the coma, which includes dust. This is still a substantial size, and indeed unusual, but it falls within the realm of possibility for a natural object. Yet the initial brightness measurement was not erroneous, it was accurate. Comet 3I 2023 Atlas genuinely appeared brighter than would be expected for a 5-kilometer comet at that particular distance. Lowe posits reflectivity as a potential explanation. If the comet's surface incorporates metallic components, if its shape focuses reflected light, or if its material properties are fundamentally different from porous ice and dust, then anomalous brightness can occur. This would result in an object appearing larger than its actual dimensions. Such characteristics could be natural. Metallic asteroids do exist. However, when considered in conjunction with all other observations, it lends further weight to the probability scale. Then there is the configuration of the dust. Hubble imagery indicates that the dust density is greatest on the sunward side of the nucleus. The heavier dust grains, those too massive to be significantly affected by radiation pressure, are concentrated ahead of the nucleus, in its direction of travel. Standard cometary outgassing processes typically produce jets perpendicular to the comet's surface, influenced by localized heating patterns. These jets can be directed in various orientations depending on the rotational axis and the distribution of volatile ices. However, sustained ejection of dust in the sunward direction necessitates either a very specific orientation of the rotation pole or an alternative mechanism. This implies something that continuously expels material in the direction of motion, irrespective of which hemisphere is facing the sun. Lowe suggests this aligns with debris ejection resulting from high-speed transit through the interstellar medium. If Comet 3I 2023 Atlas has traversed space at speeds of 60 to 70 kilometers per second for millions of years, the impacts with interstellar hydrogen atoms are not insignificant. Each impact releases energy. A sufficient number of these impacts can lead to the erosion of the leading surface. The dust observed could be impact ejecta, material continuously ablated by ram pressure as the object plows through space. This is a naturalistic explanation, but it is also consistent with venting from internal systems, the operation of attitude control thrusters, maintaining orientation, or a multitude of technological processes that could produce similar observable effects. The rotation period of 16.16 hours falls squarely within the range of ambiguity. It is too slow to be indicative of spin-up due to outgassing, and too rapid to be tidally locked to any significant gravitational body. For a rubble pile comet held together by weak gravitational forces, this rotation period is stable and unremarkable. Similarly, for a solid object, whether natural or manufactured, this rotation period is equally stable and unremarkable. It offers no definitive conclusions. However, the approach angle is more difficult to dismiss. Approaching from the direction of Sagittarius implies an origin from the galactic center. the most densely populated and brilliant region of the night sky. Detecting an object against such a luminous background is extraordinarily challenging. We only spotted Comet 3I 2023 Atlas because the Atlas survey telescopes are specifically designed to detect fast-moving objects, and even then, it was nearly missed. Pre-discovery images extend back to mid-June, but the object was barely visible at magnitude 20 a few weeks prior, meaning we would have had no observations at all. It would have traversed the inner solar system completely undetected. If one were planning a reconnaissance mission to an alien solar system, approaching from the galactic centre would represent a tactically sound strategy. The object would arrive masked by background light, providing the inhabitants with minimal warning. By the time detection occurs, the object would already be deep within the system, leaving insufficient time for any meaningful response. Is this what transpired, or are we observing a recurring phenomenon of retrofitting intent onto mere coincidence? The initial spectroscopic confusion provides an additional data point. Multiple research teams reported the absence of carbon-based molecules in the initial weeks of observation. There was no clear signature of water, only reddish dust and ambiguous absorption features. The object appeared active but not distinctly cometary. Lowe argued that this was the critical evidence, the smoking gun, proving that Comet 3I 2023 Atlas was not behaving like a natural comet. Subsequently, further observations were conducted. Water was detected. Carbon dioxide was found to be the dominant constituent in the coma. The spectral signatures began to align with cometary expectations. Lowe subsequently revised his position, but noted that the initial ambiguity remains unexplained. Why did it take so long for the comet to exhibit standard volatile signatures? Why the initial confusion? One plausible explanation is observational bias. The early spectra were low resolution, short exposures taken when the comet was still faint. As the comet brightened and more sensitive instruments were brought to bear, the data quality improved. What initially appeared as an absence of volatiles might simply have been an absence of sufficient signal-to-noise ratio. This is the less sensational explanation, and likely the correct one, though the word likely carries significant weight in that assessment. Lowe is not asserting certainty. He is advocating for thorough investigation, for acknowledging that the probability is non-zero. He emphasizes that the consequences of being mistaken, of misinterpreting a technological artifact as a comet, given that comets are common and artifacts are exceedingly rare, would be catastrophic for our understanding of intelligence in the universe. He has called for the Galileo Project observatories to conduct monitoring for secondary evidence during November and December. If Comet 3I 2023 Atlas releases probes, and if those probes enter Earth's atmosphere to conduct close-range studies of our planet, there might be an observed increase in unidentified aerial phenomena. These would manifest as objects exhibiting flight characteristics that defy conventional aerodynamics, or radar returns that do not correspond to natural objects or known human technology. Is this scenario probable? No. Lowe readily admits that the odds favour a natural comet, but the odds are not absolute, and within the space between high probability and absolute certainty lies the entire field of technosignature research. For 60 years, we have diligently listened for radio signals emanating from alien civilizations. We have constructed massive telescopes to detect laser flashes from distant stars. We have meticulously analysed millions of stellar spectra in our search for atmospheric biosignatures on exoplanets. However, we have never seriously considered the possibility that artifacts might traverse interstellar distances to reach us. That among the interstellar objects we have begun detecting in the last 8 years, there might be probes alongside natural celestial bodies. Comet 3I 2023 Atlas represents the critical test case, the object that compels us to develop methodologies for distinguishing between natural phenomena and artificial constructs at interstellar distances. Such definitive methods currently do not exist. We possess data on brightness curves, spectral analysis, and trajectory charting, but we lack a robust framework for definitively stating this is unequivocally natural, or this warrants further investigation. LOE is actively striving to establish such a framework in real time, utilizing Comet 3I 2023 Atlas as the calibration target. The mothership hypothesis itself possesses an elegance that is simultaneously awe-inspiring and deeply unsettling. It is inefficient to dispatch a single probe to a single star system. Instead, one deploys motherships on prolonged, slow trajectories between points of interest. Each mothership carries a multitude of smaller, specialized probes. As it traverses a planetary system, it releases probes designed to study specific planets. These probes are intended to be expendable, small, and cost-effective to manufacture. The mothership then continues its journey to the next star system and beyond, effectively mapping the galaxy over millions of years. From the perspective of the civilization that initiated such a mission, the return on investment is immense. A single mothership can survey thousands of systems, and critically, we would remain unaware of its approach. The mothership itself would remain dark, cold, and indistinguishable from a comet or asteroid until it commenced the release of its probes. By that juncture, it would be too late. The probes would already be in flight, en route to their intended targets, and even if we detected them, interception would be impossible with our current technological capabilities, unless we possess decades of advance warning. LOE has proposed a specific timeline. If probes were deployed on October 29th, during the obscured perihelion passage, utilizing reverse Oberth maneuvers to decelerate and achieve capture into Earth orbit, their arrival would occur between November 21st and December 5th. We are contemplating objects potentially the size of a shoebox, perhaps even smaller. Earth's space surveillance network can track objects down to approximately 10 centimeters in low Earth orbit. However, this capability is predicated on tracking objects that are expected to be present and follow predictable orbital paths. An object entering from interstellar space, possessing active propulsion and maneuvering capabilities, could easily evade detection. Would they initiate contact? Would they maintain a covert presence? Would they study us from orbit, land on the surface, or simply observe and transmit their findings back? These are the questions that preoccupy LOE's thoughts, as the answer profoundly impacts everything. If they are peaceful explorers, the xenoarchaeologists of some ancient galactic civilization, then this moment of first contact could represent the most significant event in human history. Conversely, if they represent something else entirely, if the dark forest hypothesis holds true, the notion that revealing one's location to the galaxy is tantamount to a death sentence, then we may have already passed the point of no return. The Galileo Project observatories will be actively monitoring the skies. 3 sites will provide continuous full-sky coverage. Any peculiarities observed during the November to December period will be thoroughly documented, meticulously analysed, and subsequently made public. Should nothing extraordinary occur, if Comet 3I Atlas behaves in a predictable manner akin to a comet, and no unexpected craft make an appearance, then our current hypothesis will lose its persuasive power. The assessment of its anomalous characteristics will diminish. We will then classify 3I Atlas as an object of interest, but with natural origins, and proceed accordingly. However, if an event does unfold, if we detect entities that are not expected to be present, exhibiting motion patterns that defy conventional understanding, and appearing precisely when predicted by LOE, then we face a significant challenge, or potentially a remarkable opportunity, contingent on subsequent developments. Chapter 3. October 29th, Beyond the Sun. A solar conjunction is not anticipated to be this extraordinary. Typically, comets traverse behind the Sun, become invisible for a few days or weeks, and then re-emerge on the opposite side, displaying predictable alterations, perhaps brighter if they have endured, or fragmented if they have not. Astronomers have observed this phenomenon for centuries and understand the expected outcomes, but Comet 3I Atlas is reaching its closest point to the Sun, its perihelion, at 1.36 astronomical units on October 29th, completely obscured by the Sun's intense glare. The uncertainty surrounding what transpires next is propelling the scientific community into unexplored territory. The celestial alignment is particularly challenging. Earth and the comet are positioned on opposite sides of the Sun, with an angular separation that renders ground-based observation impossible. One cannot direct a telescope toward an object located only 12 degrees from the Sun without risking damage to the instrument or permanently impairing the detectors. The overwhelming brilliance of the Sun eclipses all else. Even orbital observatories like the Hubble Space Telescope adhere to strict exclusion zones to avoid solar interference. While instruments such as SOHO and other coronagraphs might capture a fleeting glimpse, 3i Atlas is projected to be too faint and too distant from the Sun's visible edge to be discernible against the scattered light. For approximately 6 weeks, spanning from early October to mid-November, our observational capabilities are effectively nullified. However, perihelion is not solely a matter of visibility. It is fundamentally about physics. At a distance of 1.36 astronomical units, the solar radiation is sufficiently intense to vaporize every volatile compound present on the comet's surface. Water ice undergoes aggressive sublimation. Carbon dioxide, identified by JWST observations as the predominant gas in the coma, transitions directly from a solid to a gaseous state almost instantaneously. Carbon monoxide, ammonia, methane, and any other highly volatile substances trapped within the ice matrix all are released simultaneously. The comet's nucleus is expected to become a veritable pressure cooker. Gases will escape through fissures and vents, dust will be lofted by the expanding vapour, and the coma will swell to millions of kilometres in diameter. The tail will trail behind like a celestial banner. This is the prevailing model, the scenario predicted by every textbook. But this model presupposes a complete understanding of 3i Atlas's composition and internal structure. And that is not the case. Not truly. The data acquired by the JWST on August 6th revealed something unexpected. A ratio of carbon dioxide to water of 8:1. This is among the highest values ever recorded for a comet. Most comets in our solar system exhibit ratios closer to 1:1, or even a dominance of water-based chemistry. Carbon dioxide is a common constituent but is rarely the primary volatile compound. Comet 3i Atlas reverses this relationship. It is effectively a dry ice comet, with water playing a secondary role. This fundamental difference significantly alters expectations for its perihelion behaviour. Carbon dioxide ice sublimes at considerably lower temperatures than water ice. At 1.36 astronomical units, the surface temperature on the side facing the Sun could reach 200 Kelvin or even higher. This temperature exceeds the sublimation point for carbon dioxide, which begins to occur around 150 Kelvin. Water ice, conversely, requires temperatures closer to 270 Kelvin for efficient sublimation. This leads to a decoupling of the outgassing processes. The carbon dioxide erupts from the surface immediately, creating a bright, rapidly expanding coma. Subsequently, there is a slower, more sustained release of water vapour as the surface layers erode, exposing the underlying ice. However, a significant complication arises. If the carbon dioxide dominates and erupts with great force, it could potentially strip away the surface dust layers that normally act as insulation for the deeper water ice. Once this insulating layer is compromised, solar radiation can penetrate further. The rate of water sublimation accelerates. The comet could transition from a carbon dioxide dominant system to a water-dominant system within a matter of hours or days. And we will not witness this transformation in real time. We will only observe the consequences when the JWST mission gathers its observations in November. There exists another scenario, one that is seldom discussed in formal scientific papers, but is often alluded to in private conference calls. What if the comet were to fragment? The stress experienced at perihelion is a tangible force. The combined effects of thermal shock, internal pressure generated by outgassing, and the gravitational tidal forces exerted by the Sun can cause weakly bound celestial bodies to disintegrate. We have witnessed such events. Comet Shoemaker-Levy 9 fractured into more than 20 pieces before impacting Jupiter. Comet Bella split apart in the 19th century and never reformed. More recently, Comet Atlas C2019Y4 disintegrated in the year 2020 as it approached the Sun, effectively breaking apart into a cloud of debris. Comet 3I Atlas possesses a rotational period of 16.16 hours. This rate is slow enough that centrifugal forces are negligible. Gravity alone should be sufficient to maintain its structural integrity. However, this object has been traversing interstellar space for billions of years. Exposure to cosmic ray bombardment, temperature fluctuations between near absolute zero and any warmth absorbed during its passage near other stars, impacts from micrometeorites, and internal voids formed by volatile loss over vast geological timescales could have compromised its structural integrity in ways that are undetectable through spectroscopic or photometric analysis. If fragmentation occurs, the light curve will provide the evidence. A sudden surge in brightness would indicate the exposure of increased surface area. This would then be followed by a rapid decline as the fragments disperse, reducing the total observable cross-section. By the time JWST conducts its observations in November, we would likely observe multiple distinct condensations, separate nuclei, each accompanied by its own coma, strung out along the comet's orbital path. From a scientific perspective, this would be a spectacular sight. Multiple samples derived from the interior of an interstellar comet, with different layers exposed, revealing compositional gradients in stark detail. However, it would also mean that we missed the actual fragmentation event itself, the precise moment of breakup, the forces that caused it, and the manner in which the material separated. All of these critical events would have transpired behind the Sun, rendering them unobservable. Then there is Lowe's hypothesis, which posits perihelion as an opportunity rather than an inherent risk. If Comet 3I Atlas possesses technological capabilities, including any capacity for propulsion or active maneuvering, perihelion represents the optimal time to utilize them. The thrust generated by even a small amount of propulsion is amplified exponentially at perihelion. A minor burn at this point can achieve velocity changes that would necessitate orders of magnitude more fuel at a greater distance from the Sun. If the objective is to deploy probes designed to achieve stable orbits around planets, this is the moment to do so. The mathematical calculations are unequivocal. October 29th represents the ideal window. Lowe has precisely calculated the necessary parameters. A 10-kilogram probe equipped with a chemical rocket capable of providing a delta V of 500 meters per second could be inserted into a highly elliptical Earth orbit, with a periapsis around 400 kilometers and an apopsis extending beyond the Moon. From such an orbit, the probe could meticulously study Earth's atmosphere, oceans, electromagnetic emissions, and any other phenomena observable from space. It could transmit data back to 3I Atlas before the parent craft exits the solar system. Alternatively, it could remain dormant, passively observing and recording for later retrieval. The projected arrival window for such probes is late November, specifically between the 21st and December 5th, depending on the exact release point and trajectory. This estimation assumes minimal corrective maneuvers during transit. If the probes possess greater fuel reserves and more sophisticated guidance systems, the arrival window could be expanded, potentially allowing for earlier or later detection. It is also possible that they might evade detection altogether through intentional maneuvering. And here lies the unsettling question: would we even recognize them? Our space surveillance network meticulously tracks catalogued objects, satellites, space debris, and discarded rocket stages. Their positions are known, and their future trajectories are predictable based on orbital mechanics. The appearance of an entirely new object in an unexpected orbit would trigger immediate alerts. However, the response time is not instantaneous. By the time an anomaly is identified, its origin investigated, and natural explanations ruled out, the probe could have already completed its primary mission and altered its orbit once more. Lowe has specifically tasked the Galileo Project observatories with monitoring for precisely these types of events. 3 facilities are conducting continuous all-sky surveys across optical, infrared, and radio wavelengths. Any transient event, any object exhibiting motion that deviates from standard ballistic trajectories, will be flagged for thorough analysis. During the November to December window, the detection threshold will be significantly lowered. While this will likely increase the number of false positives, it will also enhance sensitivity. If something does arrive, they are positioned to detect it. NASA and the European Space Agency have not issued official statements regarding this particular aspect of the mission. Their public focus remains on the natural comet hypothesis. However, behind closed doors, considerable attention is being paid to these possibilities. Space agencies have established protocols for dealing with unidentified objects. These are not protocols for unexplained aerial phenomena or alien contact scenarios, but rather engineering protocols designed to address unexpected debris, untracked satellites, and potential collision risks. These existing protocols can be adapted. If an object appears in Earth orbit without any discernible launch history, no corresponding entry in orbital catalogues, and no plausible natural explanation for its presence, these protocols would be activated. Tracking efforts would intensify, military assets would be engaged, the international community would begin to pose inquiries. October 29th is precisely 6 days away as this recording commences. Comet 3I Atlas is already invisible, having been swallowed by the sun's intense glare. The last available ground-based observations were made in late September. Mars orbiters managed to capture images during their flyby on October 3rd, but these provided no indication of anomalous behavior. The images depicted a comet behaving normally, with a visible coma and dust production consistent with solar heating. There was nothing to suggest technology, fragmentation, or an impending crisis. But perihelion is a different matter. Perihelion is the point where thermal stress reaches its peak, where internal pressures exceed structural limits, and where critical decisions are made. If such decisions are even possible, in 6 days, Comet 3I Atlas will be closer to the Sun than it has ever been throughout its multi-billion-year existence. Its surface temperature will skyrocket, its outgassing rate will explode, and we will be completely unable to observe any of it. The only real-time data will originate from heliospheric observatories. The Parker Solar Probe is not positioned in the correct location. However, the Stereo and SOHO missions might detect something. These observations will involve scattered light and brightness fluctuations. If 3I Atlas undergoes a major outburst, if its coma expands rapidly enough, the solar monitoring satellites could register a change in the scattered solar radiation. This would be an indirect measurement, low in resolution, but it would still constitute a data point obtained during our observational blackout. Then, we must await the arrival of JWST. The spacecraft is perfectly positioned for post-perihelion observations. Between November 2nd and November 25th, it will conduct observations using multiple instruments. The Janus cameras for imaging, the MAGIS spectrometer for compositional analysis, the PET particle detector for characterizing the coma environment, and the UVS ultraviolet spectrograph for volatile identification. All of these instruments will be directed at Comet 3I Atlas as it emerges from behind the Sun, still radiating heat from perihelion, potentially fragmented, possibly trailing a magnificent tail, and quite possibly exhibiting behavior no one predicted. However, the collected data will not reach Earth until February of 2026. JWST is currently utilizing its high-gain antenna as a heat shield, relying on its medium-gain antenna for communication. The data transmission rate is slow, as observations take precedence over immediate transmission. Consequently, the images and spectra are stored on board, queued for download only when sufficient bandwidth becomes available. By the time we are able to view what JWST captured in November, Comet 3I Atlas will have already passed Venus and be on its trajectory back towards the asteroid belt, gradually cooling and diminishing in brightness. This 3-month delay translates into 3 months of speculation, debate, and competing interpretations. Did it survive? Did it fragment? Did any unusual events occur during its hidden passage through perihelion? The answers currently exist in the photons travelling from JWST to Earth at the speed of light, but we cannot access them. We cannot know the truth until the data arrives, is processed, and is officially released to the scientific community. This is the inherent cost of conducting observations at interstellar distances using spacecraft designed for our solar system. We gain unprecedented perspectives from unique vantage points, but we pay for it in time, in protracted waiting, and in uncertainty that stretches across months rather than mere hours. October 29th marks a critical turning point. Prior to this date, Comet 3I Atlas is simply a comet approaching the Sun. Unusual perhaps, but explicable, interesting, but not fundamentally revolutionary. Following this date, it will transform into whatever its perihelion passage dictates, a field of fragmented debris, a brilliantly illuminated comet with an immense tail, a dormant object that survived intact but inactive, or something entirely different, something that necessitates the creation of new categories, new terminology, and new interpretive frameworks. The Sun conceals the answer, not indefinitely, but for just long enough to make the waiting agonizing. Chapter 4. The Carbon Dioxide Anomaly. The James Webb Space Telescope observed Comet 3I Atlas on August 6th, at a distance of 3.32 astronomical units from the Sun. The NIRSPEC instrument, engineered to detect infrared signatures imperceptible to optical telescopes, recorded spectral images across a wavelength range of 0.6 to 5.3 micrometers. The resulting data was not merely unusual, it presented a chemical profile unlike anything previously observed in our catalogue of comets. The carbon dioxide to water mixing ratio stood at 7.6 to 1. For context, the next highest recorded ratio, excluding the extreme outlier C2016R2, is below 3 to 1. Comet 3I Atlas is not simply abundant in carbon dioxide. It is dominated by it to an extent that challenges our prevailing models of comet formation. Martin Cordner from NASA Goddard led the analysis team responsible for this groundbreaking research. The paper, uploaded to arXiv in late August, meticulously details the observations. The coma exhibits enhanced outgassing on the sunward side precisely as expected from solar heating. Water is present. Carbon monoxide is also detected. Carbonyl sulfide shows up in tentative detections. Water ice is evident in the spectral signatures. Dust scattering is observable in the near and mid-infrared wavelengths. All of these observations are consistent with typical cometary behavior, with the sole exception of that remarkable ratio. 7.6 to 1 is 4.5 sigma above the trend line for long-period and Jupiter family comets at comparable heliocentric distances. In statistical terms, sigma quantifies standard deviation. 1 sigma represents normal variation. 2 sigma is considered notable. 3 sigma is rare. A deviation of 4.5 sigma suggests either a significant error or a fundamental difference in the object. When deviations of this magnitude are encountered, one begins to question the relevance of the comparison sample. It is possible that Comet 3I Atlas is not an outlier, but belongs to an entirely different population, rendering our comparisons inappropriate. The carbon isotope ratios offer an additional clue. Webb detected both carbon-12 and carbon-13 in the coma emissions. The ratio between them falls within the range observed on Earth and throughout our solar system. This suggests that the carbon originated in a similar stellar environment, not from a population 3 star in the early universe with near-zero metallicity, nor from a carbon star enriched with unusual nuclear synthesis products. Instead, it indicates normal carbon derived from a standard star. However, the abundance of carbon dioxide relative to water points to a different origin, both in terms of location and the process of ice formation. 2 primary explanations exist, and both present challenges. The first explanation involves radiation processing. If Comet 3I Atlas formed within a protoplanetary disk exposed to intense ultraviolet radiation from a hot young star, or if it spent billions of years in the interstellar medium subjected to cosmic ray bombardment, the water ice could have been preferentially destroyed. Water molecules are more susceptible to breakdown than carbon dioxide molecules. High-energy photons and particles strike the ice, cleaving the hydrogen-oxygen bonds. The liberated hydrogen escapes into space due to its low mass. The oxygen can then recombine with carbon to form additional carbon dioxide. Over vast geological timescales, a comet initially rich in water could become carbon dioxide rich through relentless attrition. The problem with this explanation lies in its quantitative demands. To transform a comet from a state of roughly equal proportions of water and carbon dioxide to an 8:1 ratio favouring carbon dioxide requires extreme radiation exposure over extreme timescales. We are contemplating billions of years spent in the interstellar medium with virtually no shielding. While plausible for Comet 3I Atlas given its potential age, this scenario also necessitates that the water ice remained exposed on the surface for the entirety of that period. If the comet possesses any protective dust layer, or if its internal structure shields deeper ice from radiation, the efficiency of this processing diminishes dramatically. This would result in a gradient, with surface ice heavily processed and interior ice remaining pristine. As the comet becomes active and begins shedding layers, the ratio should change as deeper material is exposed. We have not yet observed such a change. The ratio has remained consistent between the August JWST observations and earlier spherics data. The second explanation centres on the location of formation. Carbon dioxide possesses a lower condensation temperature than water. Within a protoplanetary disk, there exists a boundary known as the carbon dioxide ice line. Inside this line, carbon dioxide remains in a gaseous state. Outside this line, it condenses into solid ice. The water ice line is situated closer to the star. If Comet 3I Atlas formed beyond the carbon dioxide ice line in a disk where carbon was unusually abundant, it could have naturally incorporated more carbon dioxide than water during its accretion. This ratio would then be intrinsically frozen into the comet's composition from its inception. This explanation requires specific conditions. A protoplanetary disk with a high carbon-to-oxygen ratio, or a disk where the temperature gradient positioned the forming comet within a zone rich in carbon dioxide ice, but depleted in water ice. Both scenarios are theoretically possible. Stellar metallicity varies, and disk structures differ, but finding conditions that yield an 8:1 ratio is not a simple matter. It requires precise tuning, a stellar system that exhibits noticeable deviations from our own in ways that might be rare but not impossible. Sphere X observations from mid-August provide corroborating evidence. The Space Infrared Telescope detected a vast cloud of carbon dioxide extending at least 348,000 kilometers from the nucleus. Crucially, there was no corresponding water cloud observed at similar scales. The carbon dioxide is escaping at a faster rate, travelling farther and dominating the coma's structure. Meanwhile, water production remained below Sphere X's detection limits, with an upper bound estimated at around 4.5 kilograms per second. This figure is an order of magnitude lower than the swift detection of 40 kilograms per second, which itself was subject to uncertainty given the distance and methodology employed. This discrepancy yields a significant insight. Detecting water is challenging. It requires specific wavelengths and specialized instruments. Swift detected hydroxyl, a breakdown product of water, not water itself. Sphere X searched for water emission lines in the infrared spectrum and found none. JWST did detect water, but in lower concentrations than carbon dioxide. Each telescope observes a distinct facet of the overall puzzle. Reconciling these findings necessitates assumptions regarding chemistry, photodissociation rates, and spatial distribution. None of these assumptions are well constrained for an interstellar comet of unknown composition. One detail from the JWST data warrants particular attention. The water emission observed at 2.7 micrometers exhibits spatial structure. It is not uniformly distributed throughout the coma. Instead, there are areas of high intensity and areas of low intensity, suggesting localized sources, perhaps jets, or pockets of water-rich ice interspersed within a carbon dioxide-dominated matrix. When these pockets are exposed to sunlight, they release water in bursts rather than through steady sublimation. The resulting spectral maps display a patchy appearance. The carbon dioxide emission at 4.3 micrometers, in contrast, appears smoother and more evenly distributed, consistent with widespread sublimation across the entire sunward hemisphere. This spatial disparity has implications for the comet's internal structure. If Comet 3I Atlas were compositionally homogeneous, with carbon dioxide ice throughout, the outgassing would be uniform. The localized emission of water suggests heterogeneity, perhaps distinct chunks, layers, or pockets of varying composition mixed together, akin to geological strata with clearly defined layers. Each stratum chronicles a distinct phase in the comet's genesis or metamorphosis. As the exterior erodes, different layers are unveiled, leading to corresponding shifts in gas expulsion. However, an alternative hypothesis exists. The localized release of water might originate from the icy detritus suspended within the coma. These are the same fragments that Swift indirectly detected by observing hydroxyl. If these pieces possess compositions differing from the main body, with some being exceptionally rich in water while others are saturated with carbon dioxide, then spatial variations become comprehensible. What you are observing is not structural features on the nucleus itself, but rather the organization within the gaseous envelope surrounding it. Hundreds, perhaps thousands of ice fragments, each acting as a miniature comet, each contributing to the overall emission in varying proportions. Differentiating between these explanations necessitates imaging of superior resolution. We must be able to resolve the nucleus distinctly. We need to ascertain whether there are active zones, jets, or specific fissures venting gas. The Hubble Space Telescope is incapable of this. The nucleus is too diminutive and too remote. The James Webb Space Telescope also cannot accomplish this. Its field of view is too confined, and the comet's rapid movement prevents detailed mapping. The JWST mission might achieve this in November, contingent on the comet's brightness and proximity, and the proper functioning of its cameras, but this remains uncertain. The tentative detection of carbonyl sulfide introduces another layer of complexity. Carbonyl sulfide is uncommon among solar system comets. It appears sporadically, typically in minimal quantities, and its presence suggests sulfur-based chemistry within the protoplanetary disk. If 3I's Atlas exhibits measurable carbonyl sulfide, it indicates that its parent star system possessed available sulfur during the planet formation era. Coupled with the predominance of carbon dioxide, a picture emerges of a star system characterized by atypical ratios of volatile compounds: high carbon, high sulfur, and low oxygen, or at least reduced water content. It's a system where the chemistry favors reduced compounds over oxidized ones. Why is this significant? Because the chemistry of volatile substances dictates habitability. A star system abundant in carbon dioxide and sulfur but deficient in water is not an ideal environment for life as we comprehend it. Water serves as the universal solvent, the medium in which biochemical processes occur. Carbon dioxide is beneficial. Plants utilize it for photosynthesis, but it cannot substitute for water. If 3I's Atlas originated in a system where water was scarce, any planets within that system would face considerable obstacles in the development or sustenance of biological life. They would be arid worlds, rich in carbon but lacking in water. These are the types of planets we've begun to discover orbiting M-dwarf stars, those small red stars that are numerically predominant in our galaxy. Is this the origin of 3I's Atlas? An M-dwarf system where the habitable zone was situated close to the star, resulting in tidal locking that scorched one hemisphere while freezing the other, where water remained scarce and carbon dioxide dominated the atmospheric chemistry. The hypothesis of formation within a thick disk lends support to this. Older stars generally exhibiting lower metallicity, though with substantial variations. M-dwarfs that formed 10 billion years ago and continue to burn steadily today, while the planets in their vicinity evolved, or failed to evolve, under harsh conditions. This is speculative. This involves filling in blanks with assumptions layered upon assumptions. However, the chemical data is irrefutable. The ratio 7.6 to 1 is not arbitrary. It is a constraint, a boundary condition that any formation model must satisfy. Meeting this requirement necessitates either extensive processing over billions of years or formation within an environment fundamentally dissimilar to the one that produced Earth. The James Webb Space Telescope observations concluded in August. The comet moved too close to the Sun for safe observation, and the telescope shifted its attention to other targets. There are no plans for further observations after its closest approach to the Sun. Observing time on the James Webb Space Telescope is precious, allocated months in advance, and the opportunity to observe Three Eyes Atlas has passed. Whatever transpires at its closest solar approach, whatever chemical transformations occur during peak solar heating, we will not witness them with the Webb. We will rely on the JWST mission and ground-based telescopes to document the aftermath. By then, the ratio of carbon dioxide to water may have shifted. The comet's chemistry may have evolved. The evidence the Webb captured in August might represent the sole snapshot we ever obtain of Three Eyes Atlas in its pre-perihelion state. This renders the data invaluable. It is a chemical fingerprint from an entity that originated in another star system billions of years ago. A record of volatile abundances reflecting conditions we cannot replicate or observe directly. And a mystery that deepens with each subsequent analysis. Because the ratio 8 to 1 is not merely unusual, it is a signpost, an indicator signifying an event that does not occur in our galactic neighbourhood. Whether that event was natural or artificial, random or deliberate remains the persistent question. Chapter 5. Mars Observes the Visitor. October 3rd, 2025. Three Eyes Atlas traversed Mars at a distance of 29 million kilometers. For perspective, this is approximately 77 times the separation between Earth and its moon. In cosmic terms, this is close. Close enough for the European Space Agency's Mars orbiters, instruments designed to photograph rust-coloured rocks a few hundred kilometers below, to pivot their sensors skyward and capture the interstellar visitor as it blazed through Martian space at 67 kilometers per second. The ExoMars Trace Gas Orbiter obtained the most compelling images. The CASIS Colour and Stereo Surface Imaging System captured a series of exposures between October 1st and 7th. The images are not remarkable by Hubble standards. Three Eyes Atlas appears as a faint white dot, slightly elongated, moving against a backdrop of star streaks. The stars appear streaked because CASIS tracked the comet, compensating for its motion relative to the spacecraft. Each exposure lasted 3 minutes. When combined, they form a rudimentary animation. The dot descends through the frame, its coma clearly discernible as a diffuse halo spanning several thousand kilometers. There is no visible tail, or at least none bright enough to register above the noise threshold. Nick Thomas, the principal investigator for CASIS, acknowledged the observation's difficulty. The comet is approximately 10,000 to 100,000 times fainter than our typical targets. Our usual targets, like Mars, are planets reflecting sunlight at close range. Aiming the same camera at a dim comet 30 million kilometers away is akin to using a microscope to observe the horizon. The instrument was not designed for such a task. The exposure durations are inappropriate and its sensitivity is marginal. Nevertheless, they succeeded. A handful of pixels, a luminous smudge. Confirmation that Three Eyes Atlas was precisely where orbital mechanics indicated, performing precisely what a comet does when approaching the Sun. Mars Express, the older of the two ESA orbiters, attempted observations, but the comet proved too faint. The high-resolution stereo camera yielded no results. The Omega and SPICAM spectrometers searched for spectral signatures, but the signal-to-noise ratio was too low for definitive detection. They may have captured something, a faint emission line, a subtle absorption feature, but the data is ambiguous, preliminary at best. The true value from Mars Express will stem from its positional context. Knowing the spacecraft's exact location, the precise moment of observation, and the exact field of view provides us with constraints. Had Three Eyes Atlas released smaller objects during its flyby, had fragments detached from the nucleus, Mars Express would have detected them. Its observation of nothing beyond the primary object indicates that fragmentation had not yet occurred. The comet remained intact. NASA's Mars orbiters were also observing. The Mars Reconnaissance Orbiter, equipped with its high-rise camera, possesses the resolution to potentially image the nucleus directly, provided the geometry was favourable. The closest approach distance of 29 million kilometres translates to a spatial resolution of roughly 30 kilometres per pixel for high-rise. Given a nucleus estimated to be between 5 and 6 kilometres, this is marginally subpixel. The nucleus would appear as a spike in brightness, a single overexposed pixel surrounded by the dimmer coma, but it should be detectable if the exposure settings were correct and the pointing was accurate. As of this recording, no high-rise images have been publicly released. This is not unusual. Processing Mars orbiter data requires time. Images are queued, downlinked when bandwidth permits, undergo calibration pipelines, and eventually are deposited in the public archives. Latencies of weeks or months are standard, but the absence of immediate release has fueled speculation. Certain internet communities insist that NASA is withholding data, claiming HiRISE observes something unexpected, and the images are being analysed privately before any public announcement. This is unfounded. NASA does not operate in such a manner. The Mars missions are public programs with established data release policies. All data is eventually made public. The delay is operational, not conspiratorial. However, the speculation highlights a significant point. Public attention is engaged. Three Eyes Atlas has captured the public imagination in ways that Comet I-1UA and Comet 2I Borisov never did. Perhaps it is the timing. Perhaps it is Leo's provocative theories, which provide a narrative framework that science fiction enthusiasts can embrace. Perhaps it is simply that social media has matured, becoming more effective at amplifying niche subjects into mainstream awareness. Regardless of the reason, the October 3rd flyby was more than just an astronomical event. It was a cultural phenomenon. Individuals who have never peered through a telescope are suddenly interested in orbital mechanics, spectral analysis, and the distinction between a comet and a manufactured artifact. Perseverance, the NASA rover situated in Jezero crater, also attempted observations. The Mastcam-Z cameras can image objects in the Martian sky, including stars, Phobos, Deimos, and the Sun during eclipses. In theory, they could capture Three Eyes Atlas if the comet was sufficiently bright and high above the horizon during the rover's operational window. On October 1st, several Mastcam-Z images captured a faint streak in the sky. Simeon Schmaltz, an astrophotographer, combined these images and enhanced the contrast. The result reveals a smudge in the location where orbital predictions placed Three Eyes Atlas. This is not conclusive. It could be a cosmic ray impact or image compression artifacts, but the position aligns, the timing aligns, and if it is genuine, it represents the only ground-level view of an interstellar object ever obtained from another planet. Avi Loeb posted about it, using it as evidence that the comet is trackable, observable, and within the reach of existing instruments if they are directed appropriately. Others countered, arguing the streak is too faint and ambiguous. Extraordinary claims demand extraordinary evidence, and a smudge in a stacked image does not meet that threshold. However, the debate itself is valuable. It compels individuals to engage with the data, to critically assess what constitutes proof versus possibility, and to grapple with the uncertainty that characterizes the frontier of discovery. China's Tianwen-1 orbiter and the United Arab Emirates HOPE spacecraft were also positioned near Mars during the flyby. Both are equipped with cameras and spectrometers and could theoretically observe Three Eyes Atlas. No data from either mission has been released to date. Tianwen-1 operates under different data sharing protocols than NASA or ESA. Images and findings are disseminated through academic papers and press releases on timelines that do not align with Western expectations. HOPE is more transparent, but its primary mission focuses on atmospheric science rather than deep space observation. If either spacecraft acquired useful data, we will eventually learn of it. However, the silence does not constitute evidence of absence. It merely reflects the nature of international space exploration, characterized by imperfect coordination and varying priorities. The Mars flyby was always destined to be a fleeting glimpse, a brief interval where geometrical alignment allowed cameras to pivot skyward before returning to their principal tasks. Yet that glimpse confirmed critical details. Three Eyes Atlas remained intact. Its coma was active and visible. Its orbit matched predictions within measurement uncertainties. There were no fragments, no secondary objects, no indication of anything other than a solitary comet on a hyperbolic trajectory, behaving as comets do. Except for one subtle detail that is not publicly discussed, but is privately considered by many, the coma was larger than anticipated. Based on the solar flux at that distance and the estimated nucleus size, the coma should have been approximately 2,000 to 3,000 kilometers in diameter. The CASIS images suggest a size of 4,000 to 5,000 kilometers. This is not a substantial discrepancy. Estimates of coma size are notoriously imprecise. They depend on exposure duration, detector sensitivity, and the criteria used to define the boundary between the coma and the background. Nevertheless, it is larger than the models predict, exceeding what would be expected if the outgassing rate scaled linearly with solar heating. Why the larger size? One explanation is that the nucleus is more active than assumed. The estimated 8% surface coverage might be conservative. Perhaps 10 or 12% is releasing volatiles, driving a larger coma than predicted. Another explanation is the contribution of the icy debris field. Those fragments dispersed within the coma, each sublimating independently, expand the effective area of outgassing beyond the nucleus itself. A third explanation, the one few wish to articulate but which surfaces repeatedly in private conversations, is that Three Eyes Atlas performed an action near Mars, released material, vented gas, or executed a maneuver that temporarily increased coma production. There is no evidence to support this third explanation. Absolutely none. However, absence of evidence is not evidence of absence, and the Mars flyby represented the final clear observation before perihelion. If any significant event were to occur, if probes were to deploy, fragments to separate, or the comet to transition from a dormant to an active state, the flyby window presented the logical opportunity. It was close enough to planets to be of interest, sufficiently distant from the Sun for maneuvers to be efficient, hidden from direct Earth observation but observable by spacecraft positioned at Mars. The fact that the Mars orbiters detected a seemingly normal comet with a slightly oversized coma is simultaneously reassuring and frustrating. Reassuring because it aligns with expectations. Frustrating because a slightly oversized coma is ambiguous enough to support multiple interpretations without definitively confirming any single one. There is one additional data point from Mars that has not yet been fully analysed. The Nomad spectrometer aboard the trace gas orbiter not only imaged Three Eyes Atlas, but also captured spectra. These spectra are low resolution, heavily influenced by scattered sunlight and instrument noise, but they are spectra nonetheless. Those observations are still undergoing processing. The team is addressing calibration issues, attempting to extract a signal from data that was never intended to capture a target this faint and this fast. If they succeed, if Nomad managed to detect spectral lines from the coma during the flyby, We will obtain compositional data from a perspective entirely different from that of JWST, Hubble, or Sphere X. It involves a different viewing geometry, a different phase angle, and different illumination conditions. Any molecules detected in the NOMAD data can be cross-referenced with earlier observations. Conversely, any molecules that should be present but are absent will become significant. The results will not be available quickly. Spectral analysis is a painstaking process, requiring months of effort to extract meaningful scientific insights from marginal data. However, the team is highly motivated. This is the kind of observation that defines scientific careers. It presents a once-in-a-lifetime opportunity to study an interstellar comet from Mars' orbit during its closest approach. If they can extract useful science from these noisy spectra, the wait will be worthwhile. Mars also provided something else, a test of tracking and coordination protocols. 3I's Atlas travelled at high speed, 67 km per second relative to the Sun, although slower relative to Mars due to orbital mechanics. Aiming a spacecraft instrument at a moving target requires precise ephemerides, real-time updates, and perfect timing. The Mars orbiters executed this flawlessly. CASS's captured the comet precisely in the centre of its field of view. This success validates the methodologies employed. It demonstrates our capability to coordinate observations across multiple spacecraft and agencies, targeting an object that offers no second chances. This is crucial for November. When JWST conducts its post-perihelion observations, coordination will be even more critical. The comet will be brighter but also more active, potentially fragmented and variable. JWST will require precise ephemerides, updated in real time based on ground observations and orbital calculations. The Mars flyby served as the dress rehearsal. JWST represents the main event, and every lesson learned from the October 3rd observations, every pointing procedure, calibration method, and data processing pipeline contributes to maximizing the scientific productivity of the November observations. 3I's Atlas has now departed from Mars. The geometrical alignment shifted. The comet moved deeper into the inner solar system, closer to the Sun and further from the red planet. The orbiters resumed their routine tasks, mapping surface features, analyzing atmospheric composition, and searching for subsurface water. The brief interruption caused by an interstellar visitor has passed, and Mars has returned to its solitary existence in orbit, awaiting its next close encounter with something from beyond. Chapter 6. Will it disintegrate? Comet fragmentation is not a rare occurrence. It is not even particularly unusual. Dozens of comets have disintegrated throughout recorded history, some spectacularly, others quietly, but all following a pattern that astronomers comprehend with reasonable accuracy. Thermal stress fractures the nucleus. Outgassing generates internal pressure. Rotation and tidal forces pull apart weakly bound material. The comet that was transforms into a comet cloud. We document this, analyze it, and add it to the catalogue of objects incapable of surviving perihelion. 3I's Atlas is under no obligation to survive. This must be stated unequivocally. It is an object held together by gravity so weak that one could escape its influence at a brisk jog. It is an object that has endured thermal cycles ranging from near absolute zero to whatever warmth it encountered during billions of years of wandering through the galaxy. It is an object that is porous, fractured, and riddled with voids where volatiles once resided before sublimating away during previous stellar encounters about which we know nothing. Its structural integrity is questionable, its cohesion is marginal. The binding force holding the nucleus intact is measured in newtons, not megatons. Therefore, the question is not whether 3I's Atlas could break apart. The question is whether it will, and the answer hinges on factors we cannot measure from Earth. Let us begin with historical precedents. Shoemaker-Levy 9 is the notable instance discovered in 1993, already fragmented into more than 20 distinct pieces strung along its orbit like beads on a necklace. The breakup occurred in 1992 during a close pass by Jupiter. The tidal forces exceeded the comet's tensile strength, causing the nucleus to pull apart. By the time we detected it, fragmentation was complete. 18 months later, the fragments impacted Jupiter in a series of collisions that left dark scars visible for months. The largest fragment released energy equivalent to 6 million megatons of TNT, not from chemical explosives but purely from kinetic energy. Mass multiplied by velocity squared, divided by 2. Physics is indifferent to our comfort levels. However, Shoemaker-Levy 9 was a Jupiter family comet, small, loosely bound, and already weakened by previous orbital passes. 3I's Atlas is larger, denser, and this is its first and only transit through the inner solar system. These are different circumstances presenting different risk factors. Comet 73, P Temple E, fragmented during its 1995 apparition, and then fragmented again in 2006. Each passage near the Sun shed fragments. By 2011, observations had identified more than 60 distinct fragments, most of them minuscule, all following similar orbits, offset slightly by the velocity imparted at separation. The original cosmic parent, though still present and circling, has dwindled, its substance worn away, its mass diminishing with every close approach to the Sun. Eventually, all that will be left is a trail of scattered remnants, a celestial cascade awaiting Earth's passage through that orbital path many centuries from now. Comet C/2019-Y4 Atlas, despite sharing a partial designation with its astronomical namesake, is entirely unrelated and met its end in April of 2020. It was nearing its initial perihelion, brightening as anticipated, igniting enthusiasm among amateur skygazers who envisioned it becoming visible to the unaided eye. Then, its luminosity abruptly declined. Within days, it transformed from a concentrated core into a diffuse collection of debris too minuscule to discern individually. The Hubble telescope captured images of this fragmentation event. The resulting fragments dispersed, faded, and vanished. The comet ceased to exist as a cohesive entity. The precise reasons for C/2019-Y4's disintegration remain unknown. It had not yet approached the Sun sufficiently for tidal forces to be significant, nor was its rotation exceptionally rapid. The most plausible hypothesis centers on thermal stress. Rapid heating on the side facing the Sun, while the opposite side remained frigid, induced differential expansion. This stress caused the nucleus to fracture. Once fissured, the sublimation of ice exploited this weakness. The pressure exerted by the escaping gases widened the cracks. This process intensified, leading to catastrophic structural failure within hours or days. Could this fate befall 3I 2019-Y4 Atlas? Absolutely. The thermal gradient during its perihelion will be extreme, with one hemisphere subjected to intense solar radiation, while the other remains in frigid shadow, experiencing minimal impact. The temperature disparity across a nucleus measuring only 5 to 6 kilometers in width could reach hundreds of degrees Kelvin, creating substantial mechanical strain. When coupled with the internal pressure generated by carbon dioxide sublimation, a process exclusively occurring at the temperatures 3I 2019-Y4 Atlas will encounter, all the prerequisites for a fragmentation event are present. However, an opposing viewpoint exists. 3I 2019-Y4 Atlas has been demonstrably active for months, with pre-discovery images dating back to at least June revealing a faint coma. This ongoing outgassing has likely released pressure and gradually eroded its surface. This slow, continuous erosion might in fact prevent a sudden structural collapse. Consider it akin to a pressure relief valve. As long as gases can escape steadily through surface vents and fissures, internal pressure is unlikely to reach critical levels. The comet sheds volatile materials at a controlled pace, losing mass but maintaining its structural integrity. Its rotation period lends support to this notion. A stable rotation of 16.16 hours Neither accelerating nor decelerating suggests balanced forces. Uneven outgassing or asymmetrical jets would impart torque, altering the rotation rate. The consistent spin implies uniform erosion and outgassing, preventing the nucleus from being torn apart by its own activity. Furthermore, its size offers an advantage. Larger cometary bodies are inherently more resistant to fragmentation. Gravitational forces scale with mass, while tensile strength correlates with cross-sectional area. For an object 5 kilometers in diameter, even one composed of loosely bound ice and dust, gravity prevails. The escape velocity is merely a few meters per second, yet sufficient to hold the rubble together against rotational and moderate outgassing forces. A significant impulse, such as a major outburst, a collision, or an exceptionally close tidal encounter, far closer than 3I 2019 Y4 Atlas is projected to experience, would be required to overcome this binding energy, unless the nucleus is already fractured and held together primarily by friction rather than cohesion. In such a compromised state, even minor stresses could trigger separation. The resulting fragments would not violently propel apart, but would drift, diverging gradually as their slightly different orbital paths cause them to separate over days and weeks. From a terrestrial vantage point, this would appear as the comet fuzzing out, its nucleus becoming less defined, its coma growing asymmetrical, and eventually multiple distinct points of light, each a fragment on its own trajectory, closely mirroring the original orbit, would emerge. Indeed, ExoMar images from October 3rd show no indication of fragmentation at that juncture. The nucleus is depicted as a singular concentration of light, but the resolution was inadequate. Had fragments separated by merely a few kilometers, Cassie would not have resolved them. They would have remained a single indistinct smudge. Definitive confirmation of structural integrity will necessitate higher resolution imaging post-perihelion, a task falling to the JWST mission. Now, consider an alternative interpretation proposed by Lowe. What if the fragmentation is not a random natural phenomenon, but a deliberate act? The appearance of a mothercraft releasing numerous probes at perihelion would be indistinguishable from a comet fragmenting due to thermal stress when viewed remotely. Multiple objects would be observed where only one existed previously, following diverging paths. Brightness variations would occur as these fragments tumbled, presenting different surface areas to the Sun. All these phenomena are explicable by natural processes, but equally by intentional deployment. The key distinction lies in the details. Natural fragments adhere to ballistic trajectories, their paths dictated solely by their velocity at separation and the prevailing gravitational field. Their future positions can be precisely predicted using Newtonian mechanics, leaving no room for surprises. Conversely, deployed probes possess propulsion and guidance systems, enabling them to alter their trajectories post-separation. The discovery of fragments deviating from predicted ballistic paths, exhibiting acceleration, deceleration, or changes in direction, would constitute an unambiguous techno-signature. Lowe has termed this the dandelion hypothesis, likening it to a mothercraft scattering seeds, each seed a probe equipped with sensors and communication capabilities. The biological analogy is intentional. Dandelions do not precisely place their seeds, but scatter them widely, relying on quantity over accuracy. Most seeds perish in unsuitable conditions, while a fortunate few find fertile ground and thrive. For a technological civilization exploring the galaxy, this strategy offers a similar advantage, deploying hundreds of probes, accepting that most will fail or find nothing of interest, while a few succeed and transmit valuable data. The cost per probe is low, but the potential rewards are immense. If 3I 2019 Y4 Atlas conforms to this model, perihelion would serve as the dispersal event, with the probes deploying and utilizing solar gravity and their own propulsion to reach target planets such as Earth, Mars, Venus, or potentially even icy moons like Europa or Enceladus, depending on the mission profile. Each probe, equipped with sufficient fuel for its specific destination, would arrive within weeks or months, initiate observations, and transmit data back to the mothercraft before it receded beyond communication range as it exited the solar system. From our perspective on Earth, we would observe what appears to be a cometary fragmentation, analyze the debris, calculate their orbits, and publish scientific papers on thermal stress and structural failure, inadvertently missing the actual unfolding narrative because we were predisposed to interpret events through the lens of natural processes. This, for Lowe, represents the nightmare scenario, not that 3I 2019 Y4 Atlas is technological, but that it is technological, and we misinterpret the evidence due to our failure to search for the correct signatures. Our centuries of comet study have ingrained in us a specific understanding of cometary fragmentation, creating a bias in our interpretations. When we encounter fragments, we instinctively attribute them to natural causes. Overcoming this bias requires a conscious effort to actively seek anomalies and meticulously track fragments beyond the scope expected for a typical cometary breakup, specifically looking for trajectory deviations, propulsive events, or any departure from ballistic motion. JWST will perform some of these analyses automatically, tracking moving targets and calculating ephemerids. If a fragment deviates from its predicted path, the tracking software will flag it. However, the software is calibrated for minor deviations attributed to outgassing, not for significant course corrections resulting from propulsion. The threshold for anomaly detection is set for natural objects, and it remains uncertain whether this threshold is sufficiently sensitive to register probe deployment. This scenario has never been tested, nor has it been necessary to consider until now. There is one further consideration: whether 3I 2019 Y4 Atlas fragments naturally or artificially, the primary scientific target is compromised. Fragments are fainter and more challenging to track. Spectroscopic analysis becomes more difficult as the signal disperses across multiple objects. The invaluable opportunity to study an intact interstellar nucleus is lost. From a purely scientific standpoint, fragmentation represents the worst possible outcome, preventing us from obtaining clean data on composition, structure, and density, yielding instead a debris cloud. Interesting in its own right, but not the pristine sample initially hoped for. Conversely, if it remains intact, if 3I 2019 Y4 Atlas successfully navigates perihelion as a single, coherent entity, we will acquire that coveted sample. JWST will observe it in November, followed by ground-based telescopes in December. We will track its passage past Venus and Earth's orbit, onward towards the asteroid belt and beyond. We will witness its fading as distance and diminished solar heating curtail outgassing, documenting the tail's evolution, the coma's dissipation, and its return to dormancy, gathering all possible knowledge before it crosses Jupiter's orbit in March and departs permanently. Therefore, the pivotal question remains: will it fragment? The answer will be revealed in November, when JWST provides its first clear post-perihelion view, allowing us to determine whether 3I 2019 Y4 Atlas remains a singular object or has become many, whether its nucleus has survived or shattered, and whether this narrative concludes with the faint dispersal of fragments, or continues with an intact comet carrying its secrets back into the cosmic void. Chapter 7: The 10 Billion Year Journey. Xavier Perez-Coutefaux and his team at the University of A Coruña meticulously traced the comet's trajectory in reverse. 10 million years of orbital integration, utilizing Gaia data on stellar positions and velocities, were employed in their quest to identify close stellar encounters that might have influenced 3I 2019 Y4 Atlas during its extensive galactic drift. Their objective was to pinpoint its origin system. Instead, they uncovered something far more unsettling. Nothing had perturbed its course. 93 potential stellar encounters were identified, with 62 classified as high confidence. Yet not a single one had altered the comet's trajectory in any significant manner. Consider the implications. 10 million years traversing the galactic disk, passing through regions densely populated with stars, dust clouds, and molecular complexes, including spiral arms where stellar density peaks and gravitational interactions are unavoidable. And 3I 2019 Y4 Atlas proceeded through it all, virtually unaffected, moving at a relative velocity of 60 km per second with respect to the local standard of rest. This speed was too great for gravitational wells to capture it, and too substantial for radiation pressure to deflect it. It was pure momentum carrying it forward along a path that has remained fundamentally unchanged for timescales exceeding the duration of human civilization. Velocity is the crucial factor. 3I 2019 Y4 Atlas is travelling at 58 km per second relative to the galactic frame. For context, our Sun orbits the galactic centre at approximately 220 km per second. Most stars in our solar neighbourhood move at comparable speeds, with variations of 20 or 30 km per second. 3I 2019 Y4 Atlas is not merely moving, it is moving distinctly. Its velocity vector diverges from the local flow, indicating it is not participating in the orderly rotation of the galactic disk. Instead, it traverses this rotation at a steep angle, suggesting an origin from a region with different kinematic and orbital properties. The thick disk is the most probable candidate, that ancient stellar population encircling the thin disk where our solar system resides. Stars in the thick disk formed early in the galaxy's history, when the Milky Way was smaller, more chaotic, and less organized into the neat spiral structure observed today. They orbit with higher velocities perpendicular to the galactic plane, plunging up and down through the disk rather than remaining confined to it. Their metallicity is generally lower, as they formed from gas that had not yet been enriched by multiple generations of supernovae. Matthew Hopkins and the Outerbridge Oxford team conducted simulations, employing population modelling based on galactic structure and dynamics. Their conclusions, published in preprint form shortly after the comet's discovery, assigned a 2/3 probability that 3I 2019 Y4 Atlas originated from the thick disk. This is not absolute certainty, but a statistical likelihood derived from trajectory analysis and velocity matching, a confidence level sufficiently high in astrophysics to warrant hypothesis formation and predictive modelling. If 3I 2019 Y4 Atlas hails from the thick disk, it is ancient. Star formation in the thick disk ceased approximately 10 billion years ago. Any comet ejected from a thick disk planetary system would have been drifting for the majority of the universe's current age. Our solar system is 4.6 billion years old. 3I 2019 Y4 Atlas could be more than twice that age, potentially having formed when the universe was less than 4 billion years old, during an era of peak star formation rates across all galaxies, when the cosmic landscape was fundamentally different from its present state. 10 billion years of exposure to the interstellar medium, 10 billion years of bombardment by galactic cosmic rays, energetic particles accelerated by supernova shocks and active galactic nuclei, striking the comet's surface at relativistic speeds. Each impact deposits energy, breaks chemical bonds and sputters atoms over geological timescales. The cumulative damage erodes surface layers, alters chemistry, and transforms crystalline structures into amorphous states. What began as pristine ice from a protoplanetary disk becomes radiation-processed material that bears little resemblance to its original composition. However, what lies deep within remains shielded. Cosmic rays penetrate only so far. The stopping distance in ice for a typical galactic cosmic ray proton is measured in meters, perhaps tens of meters for the highest energy particles. A nucleus 5 kilometers in diameter provides ample shielding depth. The interior, protected by overlying layers, remains pristine and unaltered, serving as a time capsule preserving the chemistry of a star system that formed when the Milky Way was young. This is what renders 3 Atlas scientifically invaluable. It is not merely old, it is a direct sample from the early galaxy, a fragment of a protoplanetary disk that condensed into a comet, while the thick disk was still actively forming stars. All our current knowledge of that epoch is derived from indirect observations, light from distant galaxies revealing the universe's past, stellar archaeology within the Milky Way analysing the chemistry of old stars to infer the composition of the interstellar medium at their formation, and computer simulations of galactic evolution that, while reproducing observed properties, carry significant uncertainties. 3i 2019 Y4 Atlas, conversely, is a physical artifact, not a simulation or a distant observation. It is a tangible object that telescopes can target, an object carrying chemical signatures imprinted during its formation, isotope ratios, organic molecules, and crystalline structures within the ice, all preserving information about the conditions present in that primordial protoplanetary disk. The carbon dioxide to water ratio becomes particularly significant in this context. A ratio of 8:1 is not merely unusual, it constrains the formation environment, indicating that the parent star system possessed specific characteristics, either a high abundance of carbon relative to oxygen, or a temperature gradient within the protoplanetary disk that positioned the comet's formation zone beyond the carbon dioxide ice line, but within a region where carbon was exceptionally available. Such conditions might be common in thick disk systems, or they might be rare. We lack the statistical data. JWST's 2019 Y4 Atlas is our first thick disk comet. While the sample size is 1 is infinitely preferable to 0. Prior to 3i 2019 Y4 Atlas, all our understanding of thick disk planetesimal populations was theoretical. Models predicted that these ancient star systems ejected comets and asteroids much like modern systems do, and that a fraction of these objects would wander the galaxy for billions of years, with occasional, statistically inevitable passages through our solar system. 3i 2019 Y4 Atlas validates these predictions, corroborates the models, and proves that the early galaxy was indeed forming planets and comets, engaging in the same dynamic processes that characterize star systems today. The trajectory analysis also revealed a subtle yet significant detail. 3i 2019 Y4 Atlas is moving almost perpendicular to the galactic plane, its velocity component in the z direction, indicating movement out of the plane, is unusually high. This characteristic is typical of thick disk objects. However, it also implies that the comet has been oscillating up and down through the galaxy for billions of years. Each oscillation, taking tens of millions of years, involves traversing the thin disk, venturing into the galactic halo, returning through the disk, and ascending again. A sinusoidal path that carries 3i 2019 Y4 Atlas through vastly different environments over its existence. At times, it resides in dense regions of the disk, characterized by active star formation and high supernova rates, leading to increased radiation exposure and dust impacts, thus accelerating erosion. At other times, it is in the halo, in the near vacuum between galaxies, where radiation levels decrease and impacts become infrequent, allowing the comet to enter a dormant state with minimal erosion. This cyclical passage between harsh and benign environments may explain 3i 2019 Y4 Atlas's remarkable survival for 10 billion years. The halo phases provided respite, allowing it to cease mass loss and preserve its interior from the relentless attrition of interstellar travel. Shkru, Kakarov and Avey published a comparative analysis encompassing Oumuamua, Comet Borisov, and 3i 2019 Y4 Atlas, 3 interstellar objects with demonstrably different origins. Oumuamua, originating from the thin disk, is estimated to be approximately 1 billion years old. Borisov, also from the thin disk, is roughly 1.7 billion years old. 3i 2019 Y4 Atlas, being ancient, has a median age of 4.6 billion years, but potentially much older, hailing from the thick disk. This striking diversity suggests that interstellar objects are not a uniform population, but originate from all galactic regions and span all ages, each carrying its unique history. If such diversity exists among the 3 detected objects, the full population must be vastly more varied. The Vera C. Rubin Observatory, upon its full operational status, is projected to detect dozens of interstellar objects annually, perhaps more. Each discovery will represent a unique story, an origin, and a galactic trajectory that can be traced backward through simulation. This will enable the creation of a comprehensive census, mapping the distribution of ejected planetesimals across the Milky Way, identifying which types of star systems are most prolific in ejecting material into interstellar space, and determining which galactic regions contribute most significantly to the wandering population. 3I 2019 Y4 Atlas serves as a pathfinder, demonstrating our capability for this type of archaeological endeavour, taking a comet discovered in July and, by October, formulating a plausible hypothesis regarding its origin and age. While uncertainties remain significant, with error bars spanning billions of years, the methodology is sound. Orbital integration, coupled with population modelling and chemical analysis, yields an origin story, imperfect yet improvable. Perez-Cutfo also alludes to one further implication, though without undue emphasis. If 3I 2019 Y4 Atlas has been travelling for 10 billion years, it has undoubtedly visited numerous other star systems. As the galaxy rotates and stars migrate, the comet has passed within a few light years of thousands, if not millions, of stars over this immense timescale. Some of these stars possess planets, and some of those planets may have harboured life. 3I 2019 Y4 Atlas sailed through these systems undetected or ignored, carrying its cargo of ancient ice toward its next encounter. This raises a question that few are willing to address directly. If 3I 2019 Y4 Atlas encountered other civilizations, passing through their solar systems as it is passing through ours, what transpired? Did they notice it? Did they study it? Did they dismiss it as just another comet? Or did they take a different course of action? Consider placing a beacon, connecting a sensor, utilizing it as a communication relay point for journeys across vast cosmic distances. We have no corroborating proof for any such scenario. None. However, the absence of evidence is not conclusive when discussing occurrences that may have transpired a billion years prior around stars we cannot even pinpoint. 3 Atlas could be transmitting messages, data, advanced technology, items deposited by civilizations that flourished and vanished while Earth was still an incandescent sphere of molten rock. And we would remain unaware unless we scrutinized it meticulously with intent, predisposed to entertain notions that sound far-fetched, until one comprehends the immense timelines involved and realizes that far-fetched is not synonymous with impossible. 10 billion years represents an extensive epoch, sufficient time for empires to ascend and crumble, sufficient time for species to develop intelligence and subsequently perish, sufficient time for entire stellar populations to ignite and extinguish. 3 Atlas has traversed all of that history, a silent chronicler of galactic events, and now, for a few fleeting months, it is present, passing through our solar neighbourhood, affording us a solitary opportunity to decipher whatever narrative it holds within its chemical composition and physical structure, and perhaps within modifications we have yet to discern because we are not actively seeking them. Its trajectory continues beyond Jupiter by March, then onward past the asteroid belt, beyond the Kuiper belt, past the heliopause where the solar wind recedes and the interstellar medium takes hold, back into the profound darkness, back into the unending voyage between stellar bodies. 10 billion years already traversed. Another 10 billion years await until the galaxy itself transforms beyond recognition, and 3 Atlas will still be navigating that expanse, bearing its enigmas, anticipating the next civilization to notice. Chapter 8. Scientists mount a strong opposition, Tom Statler did not sugarcoat his words. The lead scientist at NASA responsible for small solar system bodies was directly questioned about the technological artifact hypothesis during a media conference. His answer was direct and unambiguous. It exhibits characteristics of a comet. It behaves like a comet. In virtually every aspect, it bears an extremely strong resemblance to the comets we're already familiar with. The deliberate emphasis on extremely indicated this was not a cautious diplomatic response. It was a scientist drawing a definitive boundary, declaring that enough was enough. The frustration within the astronomical community is palpable. This is not due to the questions being raised. Questions are essential. They are the very engine of scientific inquiry. The frustration stems from the manner in which these questions gain widespread attention. It's about how a hypothesis with a low probability is presented by the media and social platforms as if it carries the same weight as the substantial body of evidence pointing towards a natural origin. It's about how every new piece of data, every spectral analysis, every image must first be filtered through the narrative of an alien probe before the actual scientific findings can be discussed. Chris Lintott from Oxford was even more forthright. He unequivocally dismissed the technological hypothesis as absolute nonsense on stilts, deeming it an insult to the groundbreaking work being done to comprehend this celestial object. Lintott was part of the team that traced 3 Atlas back to the dense disk of the Milky Way. He has dedicated months to analysing its trajectory, running simulations of stellar populations, and publishing findings that advance our understanding of galactic mechanics and the origins of interstellar objects. Yet, he witnesses these significant results being overshadowed by headlines about alien spacecraft and miniature probes. The scientific community's dedication to rigorous analysis is being eclipsed by speculation that requires no supporting evidence and offers no testable predictions. Jason Wright at Penn State adopted a different tactic. He authored a comprehensive blog post meticulously addressing each of Lowe's purported anomalies, examining them one by one, supported by specific datasets. Wright is not opposed to technosignature research. He actively participates in it, belonging to the community searching for evidence of extraterrestrial intelligence. However, he also operates as a meticulous scientist who upholds stringent standards. By these standards, 3 Atlas fails every examination. Let's begin with the luminosity issue. The assertion that early photometric measurements suggested an object 20 kilometers in size, thus implying it must be something else. Wright clarifies that this represents cherry-picking data. The initial observations were of low resolution, conducted when the comet was faint and distant. As superior instruments were employed with longer exposure times, the size estimations converged between 5 and 6 kilometers. This is a normal progression of observational refinement, not an enigma demanding extraordinary explanations. Consider the claim regarding the absence of cometary signatures in early spectral analyses. Wright delved into those research papers. The observations were marginal, with the signal-to-noise ratio barely exceeding the detection threshold. The lack of distinct molecular lines did not prove an unusual composition. It simply demonstrated that the comet was too dim for definitive spectroscopy at that distance. Once instruments like the James Webb Space Telescope and other major observatories focused their attention, the characteristic signatures appeared. Water, carbon dioxide, carbon monoxide, carbonyl sulfide, all precisely what one anticipates from a comet. The initial uncertainty was a limitation of observation, not an inherent physical characteristic. Regarding the trajectory probability of 0.05%, Wright independently recalculated these figures. The computation is highly dependent on how one defines a close approach. If realistic detection thresholds are applied, accounting for the fact that we can only detect objects above certain brightness levels, the probability increases significantly. The calculation is not for the odds of any random object passing near 3 planets. Instead, it's for the odds of an object bright enough to be detected passing near 3 planets. This constitutes a much less restrictive condition. While the probability remains low, it is not absurdly so, nor does it represent a 5 sigma anomaly. Then there's the matter of the dust configuration. The assertion that the sunward emission of dust necessitates active propulsion or venting. Wright references decades of cometary research demonstrating that dust distributions are inherently complex. Jet activity is never uniformly distributed. The orientation of the rotation axis plays a role. Local variations in volatile content lead to asymmetrical outgassing. The specific pattern observed in 3 Atlas might be atypical, but it falls within the spectrum of natural phenomena. Dozens of comets within our solar system exhibit similar features. No one invokes alien technology to explain them. The argument concerning the rotation period also unravels under scrutiny. 16.16 hours is unremarkable for a comet of this magnitude. It provides stability against fragmentation. It is consistent with either a rubble pile or a solid celestial body. It offers no insight into an artificial versus a natural origin, as both would exhibit similar rotational dynamics. Employing it as evidence for technology is akin to claiming a rock is artificial because it is round. Roundness can be a natural formation or the result of shaping. Rotation periods can occur naturally or be deliberately engineered. The measurement itself is neutral. Wright reserves his most pointed critique for the argument concerning the approach angle. The claim that its origin from the direction of the galactic centre, Sagittarius, was strategically advantageous for evading early detection. This is an attempt to retroactively assign intent to geometry. 3 Atlas approached from that particular direction, because that was the direction of its travel. Had it originated from Ursa Major, similar arguments would likely be made about that region being strategically optimal for some other unstated reason. This line of reasoning is unfalsifiable. Any approach direction can be interpreted as intentional. That is not scientific reasoning. It is narrative construction. However, the most substantial criticism stems from the absence of what should logically be present if the hypotheses were accurate. If 3 Atlas is a technological artifact, it ought to emit waste heat. Any active system, any electronic component, any propulsion mechanism generates heat. This heat must be radiated away. At wavelengths corresponding to a few hundred Kelvin, infrared telescopes should detect thermal emissions that cannot be attributed solely to solar heating. Numerous infrared observations have been conducted. Spitzer before its decommissioning, the James Webb Space Telescope, SphereX, ground-based infrared telescopes. All of them indicate thermal emissions consistent with a cold, icy body warmed by the sun. There is no excess heat, no anomaly, merely a comet behaving as comets do. If propulsion were involved, we should observe evidence of it spectroscopically, chemically, or through trajectory alterations exceeding what outgassing can account for. 3 Atlas has been continuously monitored since its discovery. Its orbit is known with a high degree of precision. Any deviation from a purely gravitational path would be readily apparent. There is none. The comet adheres perfectly to Newtonian mechanics. No engine firings, no course corrections, no indication of active control. If communication were occurring, we should detect it. Radio emissions, laser pulses, modulated light. The SETI community has been actively listening. Multiple radio telescopes have been directed at 3 Atlas during its approach. The Greenbank Telescope, the Allen Telescope Array, the Parkes Observatory in Australia, all have been scanning across broad frequency bands for any hint of an artificial signal. The result has been silence, complete and utter silence, not even ambiguous noise that could be generously interpreted as artificial, merely the background hiss of the universe devoid of any artificial component. Every test that could distinguish between technological and natural origins has been performed. Each test yielded negative results. At a certain juncture, the burden of proof shifts. It is no longer sufficient to highlight low probability coincidences and demand that natural explanations account for them. Positive evidence is required, a detection, a measurement, something inexplicable by cometary behavior that necessitates invoking technology. that evidence is absent. Statler articulated this point explicitly. We possess extraordinary observational instruments. We have been intensely studying 3 Atlas for months. If there were anything genuinely anomalous, anything that contradicted the comet model in a manner requiring new physics or novel classifications, we would have discovered it. The fact that we have not is, in itself, evidence, not definitive proof, but evidence carrying significant weight towards a natural origin. The scientific community's reaction has been measured, yet firm. Research papers are published, data is shared, observations continue, but there exists an unspoken consensus that the technological hypothesis no longer warrants serious consideration. It has undergone testing and failed. To continue debating it diverts attention from the genuine scientific opportunities that 3 Atlas presents. Because those opportunities are substantial, this is the inaugural thick-disk comet ever studied. It is the first object exhibiting an 8:1 carbon dioxide to carbon monoxide ratio. It is the first interstellar visitor observed simultaneously by the James Webb Space Telescope, SphereX, and Mars orbiters. The compositional data alone could refine models of planetary formation in ancient star systems. The trajectory data enhances our understanding of galactic dynamics and ejection mechanisms. Its outgassing behavior challenges assumptions about cometary activity and the distribution of volatile compounds. However, all of this is relegated to the background when the conversation persistently circles back to alien probes. Scientists are weary of this, weary of expending time debunking claims that should never have gained traction, weary of observing their diligent work being disregarded because it lacks sensational appeal, weary of the implication that they are narrow-minded for insisting on evidence before accepting extraordinary assertions. Lintot's comment about it being an insult is telling. The teams examining 3 Atlas comprise some of the world's foremost observational astronomers. They're utilizing cutting-edge instruments, publishing in leading scientific journals, and performing precisely what science is intended to do: observe, analyze, and draw conclusions based on empirical data. Yet, they are then informed that they are overlooking the obvious, that their adherence to conventional thinking blinds them to what is plainly evident. It is profoundly frustrating. There is also a more profound concern. The public's takeaway from this entire episode is that scientists dismissed the alien hypothesis without adequate investigation. This perception is fundamentally incorrect. The investigation was exhaustive. It involved multiple teams, numerous instruments, and months of dedicated effort. The hypothesis was treated with seriousness, subjected to rigorous testing, and ultimately found lacking. However, because the tests were technical in nature, and the null results did not generate widespread headlines, the public perception is that scientists are being dismissive rather than thorough. That perception is detrimental to science. It perpetuates the notion that mainstream astronomy is overly conservative, unduly fearful of paradigm shifts, and too invested in preserving established theories. And that is simply not accurate. Astronomers would be thrilled to discover evidence of extraterrestrial technology. It would undoubtedly be the discovery of the millennium, leading to Nobel Prizes, rewritten textbooks, and a complete redefinition of our place in the cosmos. The motivation exists. The will is present. What is absent is the evidence. Wright summarized this point in his blog post. The burden of proof for extraordinary claims rests with those making them, not the other way around. Science does not operate by demanding absolute certainty from natural explanations before considering alternatives. It functions by accumulating evidence and following its direction, wherever it may lead. And currently, all the available evidence points to a comet, an unusual comet, an interesting comet, a scientifically significant comet, but unequivocally a comet. 3 Atlas will be observed through November and December. JWST will arrive in February. If something truly anomalous emerges, if post-perihelion observations reveal behaviors that cannot be explained naturally, the discourse will shift. Scientists will adapt. New hypotheses will be formulated. Testable predictions will be established. This is the progression of science, driven by evidence, not conjecture. Until then, the technological hypothesis remains precisely what it has always been, a possibility with an infinitesimally low probability, unsupported by empirical data, sustained by confirmation bias rather than a foundation in observable fact. And the scientists studying 3 Atlas will persist in their work, documenting this remarkable visitor from the galactic disk, extracting every conceivable piece of information before it vanishes back into interstellar space, irrespective of the alien narrative or the accompanying headlines, because that is the fundamental nature of scientific endeavour. Chapter 9. Social media erupts. The widespread panic began on TikTok. A video posted on September 29th featured dramatic music overlaid on stock footage of comets and spacecraft. Text superimposed on the screen claimed 3 Atlas was on a collision course with Earth, that NASA was concealing the truth, and that impact was anticipated on October 22nd. This video garnered 2 million views within 48 hours, eliciting thousands of comments. Individuals began formulating contingency plans, inquiring about evacuation protocols, and checking the proximity of nuclear shelters, all based on a complete fabrication. The collision claim was easily refutable. 3 Atlas's closest approach to Earth is 1.8 astronomical units, which equates to 270 million kilometers, more than half the distance between Earth and the Sun. It never comes remotely close to our planet. The orbital mechanics are publicly accessible. NASA routinely publishes ephemerides. Anyone with basic astronomical software can verify its trajectory, but facts do not disseminate as rapidly as fear. Debunking videos received a few 100,000 views, while the panic-inducing video continued to circulate and still does, generating comments from individuals who believe October 22nd marks the apocalypse. Subsequently, claims of remote viewing emerged. An account identified as NY Crypto King posted on X, asserting they had remote viewed 3 Atlas. The post alleged the observation of internal structures, microbial life encased within ice pockets, and a signal broadcasting on frequencies yet undetected by human technology. The post included a detailed description of the interior composition, the arrangement of technological components disguised as natural materials, and a warning that probes would be deployed on October 29th to release microbes into Earth's atmosphere as part of a terraforming initiative. Remote viewing is a pseudo-scientific practice. Controlled experiments have repeatedly demonstrated its ineffectiveness. No individual can psychically perceive distant objects, yet the post gained traction nonetheless, accumulating 30,000 likes and 15,000 retweets. People treated this information as credible intelligence, constructing theories around it and cross-referencing it with other conspiracy frameworks. The claim about a signal was particularly viral. Numerous amateur radio enthusiasts began monitoring frequencies they believed might be carrying the broadcast. They found nothing, yet convinced themselves that the signal was either encrypted or employed modulation schemes beyond the capabilities of human technology. 4chan entered the discourse with a post claiming inside knowledge. An anonymous user, identifying as a European astronomer, stated that 3 Atlas was neither a comet nor a spaceship. They proposed it was a bubble of dark matter or dark energy, a remnant from the Big Bang. According to this user, the object did not reflect sunlight, but absorbed energy from the quantum vacuum. It was purportedly heading towards Earth to merge with the planet's core and initiate a dimensional shift. The post was demonstrably fictional. The physics presented made no sense. Dark matter does not form bubbles, nor does it absorb vacuum energy. Nevertheless, the post was screenshotted and disseminated across various platforms, as if it were leaked classified information. The Jeffrey Epstein connection surfaced in early October. Someone on Reddit observed that Lowe's initial significant paper on 3 Atlas was published 72 years after Epstein's birth. They calculated that the comet's discovery date, July 1st, held numerological significance. This was followed by selectively chosen correlations between orbital parameters and dates pertinent to Epstein's life, leading to the conclusion that the entire 3-Atlas event had been manufactured to divert attention from renewed interest in the Epstein files. This conspiracy theory lacked any logical coherence. Comets are not discovered on predetermined dates to serve political agendas, yet it spread nonetheless, integrated into QAnon narratives and cited as evidence of deep state manipulation. Further variations targeted Lowe directly, with posts alleging that his analysis of 3-Atlas was compromised due to his Jewish heritage, Israeli affiliations, or because Harvard University received funding from sources allegedly connected to whatever geopolitical adversary the poster wished to invoke. These were not criticisms made in good faith. They constituted anti-Semitic attacks disguised as skepticism. Lowe addressed these claims in a blog post, emphasizing that 3-Atlas exists independently of his personal identity, that the object is observable by anyone possessing a telescope, and that his ethnicity and nationality have no bearing on its physical properties. However, engaging with bigotry is an exhausting endeavor. The posts continued to proliferate. The NASA shutdown narrative emerged as a prominent talking point. In early October, the United States government experienced a shutdown. NASA's Public Affairs Office ceased updating its websites and social media channels. The issuance of press releases slowed considerably. This temporary communication blackout coincided with 3-Atlas, approaching Mars and disappearing behind the Sun. Conspiracy theorists interpreted this as a causal relationship. They posited that the shutdown was deliberate, designed to prevent NASA from having to respond to questions about what the Mars orbiters had observed during their flyby. The agency, they claimed, was suppressing data and withholding images that depicted fragmentation, probe deployment, or other phenomena they wished to keep from the public. In reality, government shutdowns are the result of political failures, not calculated concealment efforts. They occur when budget negotiations break down. The timing was purely coincidental. NASA was not hiding anything. The processing of data from the Mars orbiter typically takes weeks even under normal circumstances. The shutdown further delayed these processes, but not due to censorship. Instead, it was because staff were furloughed, interrupting the data pipeline. When the government reopened, the images were released showing a comet precisely as anticipated. However, by that point the narrative had already been established. The delay was interpreted as proof of a conspiracy, irrespective of what the eventual data revealed. Al Jazeera's Sanad fact-checking unit investigated claims circulating on Arabic-language social media. Posts alleged that 3-Atlas would impact Earth on October 22nd, that its tail would poison the atmosphere, that electromagnetic pulses from the comet would disable all global electronics, and that religious prophecies predicted this event, with the signs aligning accordingly. Sanad traced the origins of these claims to mistranslations and deliberate fabrications. They published detailed debunking analyses, complete with source citations and expert endorsements. However, these fact-checks reached approximately 10% of the audience exposed to the original false assertions. A viral post on Facebook claimed that 3-Atlas had prompted an emergency military meeting, with world leaders convening in secret. Defensive mechanisms were being initiated. Declarations attributed to anonymous Pentagon insiders suggested the celestial body posed a significant threat to national security. The online posting linked to a video on YouTube, which had garnered 3 million views and a running time of 40 minutes. A commentator explained how the comet, designated 3-Atlas, was detected by top-secret military observation satellites prior to its discovery by civilian stargazers. It detailed how its predicted path was initially concealed and how information was purportedly leaked by individuals within the system through clandestine communication channels. None of this narrative was factual. However, it was all presented with an atmosphere of suspenseful music and a tone of authority that lent it an air of believability. The religious interpretations began to gain considerable traction. Christian postings interpreted the appearance of 3-Atlas as an omen of the end times, referencing passages from Revelation and connections to the concept of wormwood. portraying the comet as a harbinger of divine retribution. Islamic posts explored similar themes through the framework of their own scriptural traditions. Hindu interpretations involve cyclical cosmic events and the appearance of divine avatars. Consequently, individuals from diverse belief systems were projecting apocalyptic scenarios onto an object that was, in reality, merely a celestial body composed of ice and rock. The inherent human drive to find significance in astronomical phenomena is an age-old tendency. Comets have historically been viewed as portents. 3 Atlas was no different in this regard. The crucial distinction, however, was that in the present era, such omens could disseminate globally within mere hours, a stark contrast to the years it once took for such interpretations to permeate societies. The pervasive influence of meme culture also played a role. Images of 3 Atlas were circulated, labelled with various humorous or symbolic associations. These included visual gags like the forgotten homework assignment finally resurfacing, personal problems arriving precisely on schedule, or extraterrestrial visitors deciding Earth wasn't worth a stop on their tour. While these memes were largely innocuous and often amusing, they inadvertently reinforced the perception of 3 Atlas as a character within a narrative rather than a subject of scientific study. This imbued the comet with a sense of agency, intent, and even personality. This anthropomorphization made it increasingly challenging for people to engage with the actual scientific data. Individuals were connecting with the comet on an emotional level, bypassing analytical consideration. The divergence in perspectives was profound. On one side were astronomers and science communicators diligently disseminating accurate information, including spectral analysis, orbital calculations, and compositional assessments. On the other side, a vast wave of conjecture, conspiracy theories, fear, and unfounded hopes surged. These 2 groups had minimal overlap, inhabiting distinct informational spheres, utilizing different digital platforms, and adhering to divergent standards of evidence and knowledge. It was entirely possible for someone to spend extensive periods engrossed in content about 3i Atlas without encountering a single verifiable fact. Community notes on X, formerly Twitter, made efforts to moderate this flow of misinformation, adding context to trending posts, providing links to NASA resources, and presenting orbital data to refute claims of an impending collision. However, these corrections were appended only after a post had already achieved viral status, meaning the corrective information reached only a fraction of the initial audience. Furthermore, the power of motivated reasoning is undeniable. Those predisposed to believing in the hypothesis of an alien mothership found ways to disregard any contradictory evidence. They dismissed NASA as deceitful, scientists as narrow-minded, and claimed the official explanations were inconsistent. Anything that challenged their preferred narrative was systematically filtered out. YouTube evolved into a digital battleground. Scientific channels endeavoured to explain the true nature of 3i Atlas, the observable phenomena, and the implications of its chemical makeup. These informative videos struggled to surpass 100,000 views. In contrast, channels dedicated to conspiracy theories, employing dramatic thumbnails and sensationalistic titles, amassed millions of viewers. The platform's algorithm prioritized engagement over accuracy. The efficacy of fear in driving engagement far exceeded that of education, leading to the promotion, amplification, and monetization of misinformation. Reddit communities fractured along predictable lines. Subreddits focused on astronomy and space maintained a degree of scientific integrity, with moderators actively removing conspiracy-laden posts and users engaging in civil discussions, often backed by citations, concerning orbital uncertainties and spectroscopic methodologies. Conversely, other subreddits dedicated to UFOs, conspiracy theories, and fringe subjects devolved into echo chambers. Any expression of skepticism was met with downvotes, and links to mainstream scientific discourse were dismissed as state propaganda. These communities engaged in a process of self-radicalization, convincing one another that they alone possessed the truth, while others were either ignorant or complicit. Instagram influencers, lacking any formal scientific background, confidently expounded on their understanding of 3E Atlas. Many of them committed fundamental factual errors, conflating astronomical units with light years, asserting the comet's naked-eye visibility when it was never so, and confusing 3 Atlas with other celestial objects. Despite these inaccuracies, they commanded substantial audiences, with hundreds of thousands of followers who placed their trust in these influencers, sharing their content and equating the influencers' speculative pronouncements with peer-reviewed scientific research. This widespread misinformation had tangible repercussions. Astronomy educators found themselves fielding distressed emails. Teachers worked to reassure students who feared the world was on the brink of collapse. Mental health professionals addressed anxieties exacerbated by apocalyptic narratives. The impact was not theoretical. It was measurable and quantifiable in the lost time spent refuting falsehoods and the psychological distress inflicted upon vulnerable individuals. Some of the conspiratorial thinking was a form of performative trolling, perpetrated by individuals aware of the inaccuracies, but motivated by the enjoyment of creating disruption. However, a significant portion stemmed from genuine conviction. True believers were utterly convinced that 3I Atlas represented either an inaugural encounter with extraterrestrial intelligence, an existential threat, or a manifestation of divine intervention. These individuals intensified their adherence to their beliefs when confronted with contradictory evidence, actively seeking out information that reinforced their existing viewpoints, and constructing elaborate theories that link 3I Atlas to other conspiracy narratives. The celestial object effectively became a symbol, a blank canvas onto which people projected their deepest fears, hopes, and fantasies. By mid-October, 3 Atlas had transcended its identity as a mere comet. It had transformed into a cultural phenomenon, a mirror reflecting how contemporary society navigates information in the age of social media. It illuminated the blurring lines between truth and fiction, the devaluation of expertise, and the accelerated spread of fear over understanding. The actual physical object, a 5-kilometre sphere of ancient ice and rock currently obscured from view behind the sun, had become almost peripheral to the swirling narrative surrounding it. The scientists diligently studying 3 Atlas could only observe this unfolding situation. While they could publish research papers, grant interviews, and issue corrections, they were powerless to control the overarching narrative. The story had broken free, mutated, and evolved into something beyond their influence. Their only recourse was to continue their work, meticulously documenting their observations, analysing the collected data, and trusting that in the long run, long after the social media fervour subsided, the scientific record would endure as an accurate and preserved account, serving as a counterpoint to the prevailing chaos. Chapter 10: November's Moment of Reckoning. The JWST spacecraft was positioned at a distance of 428,000 kilometres from 3 Atlas on November 4th. This proximity was closer than any other spacecraft would achieve during the post-perihelion observation window. The Jupiter Icy Moons Explorer, or JWST, was not initially designed for cometary observation. Its primary purpose was to study Europa, Ganymede and Callisto, their icy crusts overlying subsurface oceans, the radiation environment surrounding Jupiter, and its magnetic field interactions. However, spacecraft possess inherent adaptability, and mission planners have the flexibility to redirect their objectives. Consequently, between November 2nd and November 25th, JWST would dedicate observational time to this interstellar visitor, gathering data at a crucial juncture when ground-based telescopes still face significant challenges due to the comet's proximity to the Sun. Its instrument suite was exceptionally powerful. Janus, the optical camera system, was poised to capture images of the nucleus and coma with a resolution unmatched by any other spacecraft during this specific period. Magis, the imaging spectrometer, would meticulously map the comet's composition across infrared wavelengths, meticulously tracking the distribution of various volatile substances within the coma. UVS, the ultraviolet spectrograph, was set to detect emissions from excited atoms and molecules, building upon the foundational observations made by the SWIFT spacecraft in August, but with enhanced spectral resolution. PEP, the particle environment package, would measure the plasma and neutral gas surrounding 3 Atlas, meticulously documenting the intricate interactions between the solar wind and the comet's outgassing. This constituted the critical observational window. 3 Atlas had emerged from its perihelion, the point closest to the Sun, on October 29th. Whatever processes had occurred during this intense solar proximity, the maximum heating, the peak outgassing, the potential for fragmentation or probe deployment, the evidence would become discernible in November. The comet was expected to be exceptionally bright and active, possibly exhibiting signs of significant change. JWST would document these transformations from a vantage point that terrestrial instruments could not replicate. However, a significant constraint loomed: communication bandwidth. JWST was utilizing its medium-gain antenna because its high-gain antenna was currently serving a dual purpose as a heat shield. This resulted in reduced data transmission rates, necessitating the onboard storage of images and spectra for subsequent download when communication windows allowed. The observations captured in November would not reach Earth until February of 2026, introducing a 3-month delay. During this extended period, scientists would remain unaware of JWST's findings, whether the comet had survived intact, if it had fragmented, or if any unexpected anomalies had appeared in the collected data. Ground-based observatories were slated to begin observing 3I Atlas in late November, once the solar elongation increased sufficiently to permit twilight observations. As the comet moved away from the Sun's intense glare and became accessible to large aperture telescopes, predictions regarding its apparent brightness varied. Some models indicated a magnitude of 10 or 11, a level bright enough to be observed by 8-inch amateur telescopes under dark skies. Other, more conservative models predicted a magnitude between 12 and 13, necessitating the use of professional instruments or specialized amateur equipment. The comet's brightness would serve as an immediate indicator of any major event. If 3 Atlas exhibited a dramatic increase in luminosity, suggesting that its perihelion passage had triggered a significant outburst or exposed fresh volatile materials, its magnitude would exceed initial predictions. Conversely, if it fragmented, its overall brightness might initially increase as more surface area became exposed, followed by a decrease as the fragments dispersed. If it entered a dormant state, with its volatile reserves depleted or its activity abruptly ceasing, it would appear dimmer than anticipated. All these potential scenarios would become apparent within the first few nights of ground-based observations. The observatories associated with the Galileo project were fully operational, with 3 sites continuously monitoring the sky, in Massachusetts, Pennsylvania, and Nevada. Throughout November and December, detection thresholds were deliberately lowered. Any transient object, any unidentified moving target, would be flagged for immediate investigation. Lobers had been explicit about his expectations. He posited that if probes were deployed during perihelion and employed reverse orbital maneuvers to enter Earth's orbit, their arrival would occur between November 21st and December 5th. The observatories were specifically tasked with searching for such entities, small objects exhibiting unusual orbital trajectories, paths that did not correspond to catalogued satellites or space debris, and anything indicative of an artificial origin. The probability of such an occurrence was acknowledged by all parties to be exceedingly low. However, the cost associated with this diligent observation was deemed minimal when weighed against the potential magnitude of the discovery. If any such object were to appear, one that defied natural explanation, the implications would be immediate and profound. Every telescope on Earth would redirect its focus towards its study. Space agencies would initiate urgent planning for interceptive missions or close-range observations, and the global scientific community would mobilize with an intensity unseen since the initial detection of gravitational waves or the definitive confirmation of an exoplanet. Conversely, if nothing of the sort materialized, if November and December passed without any probes appearing, then the technological hypothesis would lose its last vestiges of support. The Lober's scale rating would decrease, and 3 Atlas would be definitively classified as a natural comet, albeit an unusually large and chemically anomalous one, but undeniably natural. The era of speculation would conclude, and scientific inquiry would proceed. The narrative would shift from one of alien contact to one of discovery and characterization. The Europa Clipper mission was also positioned for potential observational contributions. NASA's mission to Jupiter, launched recently, was en route to its destination but had not yet reached the Jovian system. Discussions were underway regarding coordination between Clipper and JWST. Both missions were equipped with ultraviolet spectrographs capable of observing 3I Atlas simultaneously from 2 distinct locations. This would enable parallax stereo observations, providing 3-dimensional information about the comet's structure that a single spacecraft could not acquire. While the geometrical alignment might not be ideal, and Clipper's position was not optimally suited, mission planners were prepared to capitalize on any available opportunity. The truly significant scientific insights would stem from comparing the comet's pre- and post-perihelion states, data collected in August by the James Webb Space Telescope, and in September by Mars orbiters had captured 3I Atlas as it approached perihelion, while it was still relatively cool and exhibiting moderate outgassing rates. The November data from JWST and terrestrial telescopes would reveal the aftermath of this intense solar encounter. The comet, subjected to peak heating, stress, and potential transformation from the closest solar approach in its 10 billion-year existence, would be examined. Comparing these datasets would illuminate how interstellar comets respond to perihelion conditions, how their chemical compositions evolve, and how their structural integrity is maintained or compromised under extreme thermal stress. The ratio of carbon dioxide to water was of particular interest. In August, this ratio stood at 8:1. The question was whether this ratio would persist in November. Alternatively, it was possible that the perihelion heating had preferentially driven off the carbon dioxide, exposing the water ice and shifting the ratio towards a more typical composition. A change in this ratio would strongly suggest that the comet possesses a layered structure, with outer layers rich in carbon dioxide and an interior composed primarily of water ice. If the ratio remained constant, it would indicate a homogeneous composition throughout the object. Both outcomes would yield valuable scientific data, but they would tell vastly different stories about the comet's formation and evolutionary history. The development of the comet's tail was another critical diagnostic. Pre-perihelion images had depicted a faint tail, or no tail at all, depending on exposure times and instrument sensitivity. Post-perihelion, the tail was expected to be prominent, extending for millions of kilometers, its curvature influenced by solar radiation pressure and the comet's orbital velocity. Spectroscopic analysis of the tail's composition would reveal the types of dust grains being ejected, including silicates, organics, and ices. The distribution of grain sizes would provide information about the erosion processes at play. The presence of small grains would indicate vigorous sublimation, while larger grains would suggest mechanical disruption or explosive events. If 3 Atlas had fragmented, its tail would exhibit increased complexity, characterized by multiple streams and overlapping structures, with each fragment contributing its own tail. These individual tails would merge in ground-based images, but might be resolvable through careful photometry and positional measurements. Theoretically, the Hubble Space Telescope could image the tail structure if observation time became available, enabling the resolution of individual fragment contributions and the mapping of debris distribution. However, Hubble observation time is a highly precious and oversubscribed resource, with demand exceeding availability by factors of 5 to 10. Securing directors' discretionary time for such follow-up observations was far from guaranteed. The Vera C. Rubin Observatory, although not yet operational with its first light expected months away, held the promise of revolutionizing the detection and characterization of interstellar objects. Originally named the Large Synoptic Survey Telescope, it would conduct comprehensive scans of the entire visible sky every few nights, employing deep exposures and automatic detection of moving objects. The Rubin Observatory was anticipated to capture interstellar visitors at an earlier stage, while they were still distant from the Sun and faint. It would track their trajectories through perihelion and beyond, constructing light curves with thousands of data points. Subsequent spectroscopic follow-up observations by other instruments would be informed by the detailed photometric data obtained from Rubin's continuous monitoring. 3 Atlas served as a crucial prototype, an object that would provide invaluable lessons regarding future interstellar comets, their expected brightening patterns, the evolution of their activity, and the emergence of specific spectral features. Every observation of 3 Atlas would contribute to refining survey designs for the Rubin Observatory, improving detection algorithms, and calibrating existing models. The subsequent interstellar comet, the 4th to be discovered, would undoubtedly be detected more rapidly and characterized with greater accuracy due to the knowledge gained from this current object. The November observations were also vital for trajectory refinement. Each positional measurement served to enhance the orbital solution, reduce uncertainties, and enable more accurate predictions of 3 Atlas's location in December, January, and subsequent months. As the comet moved past Venus and Earth's orbit, continuing its journey back towards the asteroid belt, tracking its path would become increasingly challenging. It would dim, and its position would shift against increasingly crowded stellar backgrounds. Precise ephemerids were essential to ensure its continued visibility, allowing ground-based telescopes to point accurately and preventing the waste of valuable observing time searching for an object that should be within the field of view but is not due to minor discrepancies in its predicted coordinates. The measurements of the plasma environment by JWST were unique, as no other spacecraft was expected to achieve sufficient proximity to sample the interaction region where the solar wind directly interfaces with cometary outgassing. This boundary, often referred to as the cometary bow shock, is a dynamic zone, constantly fluctuating as outgassing rates change and solar wind pressure varies. The PEP instrument would measure ion densities, electron temperatures, and magnetic field perturbations, all of which would contribute to models of cometary magnetosphere operation, the acceleration of charged particles, and the deposition of energy into the coma. Specifically concerning 3I Atlas, the plasma data might reveal subtle compositional details. Different volatile substances ionize at varying rates, producing distinct ion species. The mass spectrometer component of PEP could differentiate between ions originating from water, carbon dioxide, and other molecular groups. The appearance of unexpected species, or if the plasma composition indicated molecules not detected through spectroscopic analysis, would constitute new and significant information, providing additional constraints on the object's actual composition versus what had been inferred from remote observations. February of 2026 felt like a distant point in time. 3 months represented a considerable waiting period for the data from JWST, but it was a necessary one. The spacecraft possessed limited communication bandwidth, and scientific integrity took precedence over public relations efforts. The forthcoming data was anticipated to be well worth the wait, meticulously processed, calibrated, and analyzed by experts possessing a deep understanding of the instruments and the expertise required to extract meaningful signals from noise. When the findings were eventually published, they were expected to be definitive, representing the most comprehensive post-perihelion characterization of 3I Atlas achievable with current technological capabilities and mission constraints. Until then, reliance would be placed on ground-based observations, the efforts of amateur astronomers equipped with backyard telescopes, professional observatories managing to incorporate 3I Atlas into their already crowded schedules, and spectroscopic campaigns organized through international collaborations. Every clear night held significance, and every observation contributed to the accumulating dataset. Gradually, image by image, spectrum by spectrum, the narrative of what transpired at perihelion would begin to coalesce. The comet remained indifferent to human curiosity. It was unaware of being observed. It simply continued its trajectory, whether outgassing or dormant, intact or fragmented, or, against all probability, something else entirely. 3 Atlas navigated through November, utterly oblivious to the telescopes tracking its path, the instruments dissecting its light, and the fervent debates surrounding its true nature. It simply existed. And humanity, from its minuscule vantage point 93 million miles from the Sun, endeavoured desperately to comprehend the meaning of its existence before the comet vanished into the darkness, taking its answers with it.